Okay, so it's 10 o'clock. Hopefully you guys can hear me. So I think what we're going to do is we're going to make a start. So good morning and welcome to Elite Medics. So this is our year 13 chemistry class on chemistry, okay? Well, I've already said that. So this is year 13 chemistry class on amides, amino acids, and proteins, okay? And just so in case some of you guys haven't been to one of our classes before, my name is Matt. I'm a third year medical student at the University of Nottingham. And, you know, I really enjoy teaching. And that's one of the reasons why, you know, we find ourselves here today, revising some year 13 chemistry. So hopefully I'll be able to cover a topic today, help you guys understand it better, or for those of you who already covered it, maybe revise it. And then hopefully that will really help you in getting into medical school or getting into university, whichever you decide to do. So then, without further ado, let's start talking about what we're going to be covering today. So I said we're going to cover amines, amino acids, and proteins. So these are three main topics that we're going to cover today. And I'm sure some of you might be delighted to know that these aren't necessarily the hardest topics in year 13 chemistry. So it will be a bit more of a casual or relaxed lesson. Before we start off with our first block, which is amines, I'd just like to cover the basic structure of what we're going to be doing today. So we've got our first teaching block, and that's from 10 a.m. to 11:30 a.m. So that's 1.5 hours. And then we have a short 5-minute break at 11:30 to 11:35. And then we have a second teaching block from 11:35 to 12:30. And then we have a 1-hour lunch break at 12:30, and we finish off the day with a 1:30 to 3 p.m. final teaching block. Okay, so don't worry, you don't have to keep timing. I will remind you guys and let you know when you can take a break, when we've got lunch, things like this. Okay, and just a note as well, we'll be covering AQA, EdXL, and OCR exam boards in this lesson, and I think for all of our lessons really, we cover these 3 exam boards. We make sure to pick the topics just so it covers everything for everyone. But of course, we do have the specifications coming up in a second for each individual exam board that we cover, just so you can double check that you know what you're doing. Also, another little note before we get started is usually what we do is we have some theory, we have some past paper questions, and we have Microsoft Teams quizzes. But today, and from today onwards, in fact, we're going to be using something called Slido. So you might have already come across it at school. Might be something you use. But essentially what it is kind of like a live polling or live questioning resource that allows us to kind of interact as a whole group on one particular question at a time. So it's a bit more interactive, a bit more fun than our Microsoft Teams quizzes. So I'm sure you guys will like it, but we'll have them coming up in a second. And I'll try to incorporate them as often as possible, like every 10 or 15 slides, just so you guys, you know, keep engaged, and it makes it probably a little bit more fun than, you know, just talking over chemistry on a Sunday morning. So hopefully you guys will enjoy that. So then, let's have a look at our learning objectives for today. So this is our learning objectives for amines. So we want to know the functional group of amines and how to name them. We want to know the properties of primary amines, including boiling points and solubility. We want to know how to make amines, both linear and cyclic. We want to understand the reactivity of amines and how their structure causes this. We want to know that amines behave as Bronsted-Lowry bases. Don't remember if you don't know what Bronsted-Lowry bases are. I'll cover it when we get to that point. We also want to know how amines' basic strength differs from each other and ammonia, essentially. And then finally, we want to be able to describe and draw the nucleophilic reactions of amines, okay? So then, as I said, we've got our specifications here for our exam board. So we've got AQA. So our AQA specifications are as follows. If you want to take a screenshot of this or maybe take a picture of it, that probably be quite useful. Just so you can, you know, always reference back to this. Okay. We also have our OCR exam board. Again, if you want to take a picture of this, please do. We make things easier. And finally, we have our Edexcel exam board, okay? So then, without further ado, let's start off with amines. Okay, so amines are molecules that contain a nitrogen atom, okay? And the easiest way to think of amines is as near relatives of ammonia, which is NH3, okay? And NH3 looks something like this. Okay, so we can already see the very similar structure when we look at primary amines, secondary amines, and tertiary amines, okay? So these can basically be thought of as deriving from ammonia, okay? So in amines, the hydrogen atoms in the ammonia have been replaced one at a time by hydrocarbon groups, okay? And those can be something like an alkyl group. So for now, we're looking at only cases where the hydrocarbon groups are simple alkyl groups, but we will get into a few more in the next slide. We'll get into a few more complexities, okay? So looking at primary amines, only one of the hydrogen atoms in the ammonia has been replaced with an alkyl group. So we've got this R group here, and R is the rest of the molecule, or, you know, an alkyl group, okay? It's probably just as worth noting that, alkyl, okay? So alkyl group. So one of these hydrogen atoms has been replaced by an alkyl group in a primary amine. And then when we look at the secondary amine, two of the hydrogens have been replaced. Okay, so you've got two R groups, R1 and R2, and we've only got one hydrogen left here. Okay, and at this level, you're only likely to come across very simple ones where both of the alkyl groups or the hydrocarbon groups are the same. You can get different ones, but at this level, at A level, you're generally going to come across where the R groups, these R1 and R2s, are the same. Okay, and then again, we have tertiary amines. And in this case, all the hydrogens have been replaced by these R groups. So you've got R1, R2, and R3. Okay. So again, at A level, we're probably going to come across tertiary amines where all of these three R groups are the same. It's unlikely that you'll come across extremely complex looking molecules or looking tertiary amines or secondary amines. Okay, so that's obviously good to know. So now that we have a basic idea of what amines are, let's have a look at how we name them. Okay, so our basic idea, just to recap quickly, basic idea is that amines are molecules that contain nitrogen ions, atoms. You can see this here, and they're basically thought of deriving from ammonia. Okay, and primary amines, they have one hydrogen replaced by an R group or an alkyl group. Secondary is 2, tertiary is 3. Okay, that's a very, very basic information that we need to know about amines. Okay, so let's get on to naming amines. Okay, so naming amines involves us using the amine suffix. Okay, the suffix means that we put it on the end. Okay, a prefix means pre, so it's at the beginning. Suffix is at the end. Okay, so we have a few examples of naming primary amines here. Okay, and remember that primary amines are those that only have one R group. Well, that means they have two hydrogens attached to the nitrogen, okay? So here we've got methylamine, ethylamine, and phenylamine, okay? Methylamine because we've only got a CH3 group attached. Ethylamine because we have an ethyl group attached, you know, C2H5. And then phenylamine because we have this benzene ring, okay? We've got this benzene ring attached, okay? Which goes under the prefix of phenyl, okay? So these are relatively simple ones to name, okay? So let's have a look at a few more complex examples. And in this case, we're moving on to the realm of secondary and tertiary amines. Again, we use the suffix amine, and the carbon chains are regarded as alkyl or aryl groups, okay? So in this case here, we've got dimethylamine, trimethylamine, and ethylmethylamine, okay? So then, dimethylamine is relatively self-explanatory, okay? So we have two methyl groups and our nitrogen and one hydrogen. And this means that this is a secondary amine, okay? So we've got one hydrogen, we've got two alkyl groups, okay? Then we have trimethylamine. This time we have 1, 2, 3 methyl groups, okay? And this means that there's no hydrogens left on this nitrogen, okay? And this means that we've got a tertiary amine. And finally, we've got ethyl methylamine. And although this one isn't the same, so the R groups are not the same, it is a fairly simple structure, okay? And we can see how we name this, okay? So it's ethyl methylamine, okay? So then, let's have a look at some of the properties that amines have, okay? So the first one that we have is this pyramidal shape, okay? And we can see this on this diagram here, okay? And we have this pyramidal shape due to the lone pair on the nitrogen atom, okay? We can see this here. So if it was a perfect pyramidal shape, let's say if we just had a structure like this, and these weren't, there were no electrons, these are just atoms, so let's say they were just hydrogen atoms. What would we expect the angle, the bond angle for these to be, okay? We'd expect it to be equal, okay? So it'd be 120 degrees here, okay? But in the case of amines, we have this nitrogen, okay, and it has this electron, a spare pair of electrons on the top, okay. Instead of this atom here, we have a spare pair of electrons, and this means that it repels these groups here even further down, okay. So in actuality, we have a smaller bond angle than 120 degrees, okay. We have 107 degrees, and this is not what you'd expect on a perfectly symmetrical pyramid, okay? So our second property that we need to know about is their polar molecules, okay? So amines are polar molecules, and this is all, again, because of this lone pair of electrons, okay? So amines can form hydrogen bonding between delta negative nitrogen, because this is delta negative because it's got its spare pair of electrons, and a delta positive hydrogen in water, okay? And this allows smaller amines, primary to tertiary, so smaller tertiary and small primary and small secondary, of course, to be soluble in water, okay? And in fact, primary and secondary amines can actually H bond with each other as they already have one or two hydrogen bonds within their structure, okay? Tertiary amines can't do this because, of course, all three of their hydrogen groups have been replaced by alkyl groups, okay? So finally, another property that we're going to look at is smell, okay? And in terms of smell, the smaller amines and, so the very small amines smell like methylamine and ethylamine smell very similar to ammonia, okay? But if you compared the smells side by side, the ammonia would, sorry, the amines would smell a little bit more complex, okay? As the amines get bigger, okay, they tend to smell a bit more fishy, a bit more like rotten fish, or like rotten flesh, okay? So this is quite a distinct property or characteristic that amines have that sometimes allows you to differentiate between other molecules as well, okay? So then, another property, well, that we've already talked about really is this hydrogen bonding, okay? So hydrogen bonds can form with themselves, water, and alcohols, okay? And here's basically a diagram that shows us this, this hydrogen bonding. So here we've got our delta negative nitrogen, and we said it's delta negative because we have this electron pair, this lone pair of electrons. And this actually causes the hydrogens on amines to be delta positive. So essentially, what we can get here is because there's a polar, these are polar opposites, we get a hydrogen bonding between the delta negative nitrogen and the delta positive hydrogen on another amine. And again, this can only happen if this is a primary, this is a symbol for primary, or a secondary amine, okay, because they have hydrogen bonds, okay. Otherwise, if you've got a tertiary amine, it can still form hydrogen bonds, but just not with itself, okay? It can form hydrogen bonds with water. So if we had something like, if you had our water molecule, that's H2O, to be delta negative, and these would be delta positive. In this case, we could have hydrogen bonding here between those, or between the oxygen and the hydrogens, okay? So that's the hydrogen bonding in a little bit more detail. So in terms of other physical properties, we have boiling points, and it's probably a good idea for us to talk about these, okay? So they find themselves between alcohols and alkanes, okay? So amines have greater boiling points than alkanes, but lower boiling points than alcohols, okay? So if we compare a few here, we've got methanol, methylamine, and ethane, okay? And these all have very, very similar molecular masses, okay? And if we have a look at the boiling points, 338 degrees Kelvin for methanol, which is our alcohol. Our methylamine has a boiling point of 267 degrees Kelvin, and our ethane, which is our alkane, has a boiling point of 185 Kelvin, okay? So you can see that the kind of wedge between alcohols and alkanes in terms of boiling point. So short-chained amines are gases at room temperature, okay? So, you know, if we have a very small, so like something like methylamine, these are usually gases, okay, because the boiling point is lower, and at room temperature, this means that, you know, they are in a gaseous form. Slightly longer amines are actually volatile liquids, okay? So they will be liquid, but a volatile liquid means that, you know, although you have a liquid, you know, the molecules on the surface of the liquid are quite prone to evaporation, okay? So slightly longer amines are volatile liquids at room temperature, okay? So as we said before, short primary amines, so like 1 to 4 carbons, okay, are very soluble in both water and alcohols, okay? And this is because we've got that H bonding between the water and the alcohols, okay? And amines are soluble in less polar solvents, okay, because water is, you know, relatively polar, and the same with alcohol, okay. But they are, because of this H bonding property, they are soluble in less polar solvents, okay. Larger amines, though, are less soluble, okay, because, you know, they're more bulky. The chances of them being soluble in water or alcohols reduces as they get bigger, okay? And amines attached to benzene rings are not soluble at all, okay? So here we've got an example, which is our phenol amine that we've seen before. So you've got our benzene ring here, okay? And for reasons that we'll actually get into a little bit later, this isn't very polar at all, okay? Because this benzene ring, remember, if you were in our lesson, we talked about other sections of organic chemistry going over benzene and phenol groups. Essentially, this phenol group is very, very stable, okay? And, stable, spell that wrong. So this phenol group is stable, and that means that it's less soluble in water, okay? So amines attached to benzene rings are not soluble in water or alcohols. Okay, so what I'm going to do now is I'm going to go and quickly recap over all those things, and then we're going to start off with a Slido, okay? It starts with our first Slido, sorry. So then, back to the beginning. Let me clear the ink from the slide. In fact, let's just do all of it. So then, amines are molecules that contain a nitrogen ion. We can see this here, and they have also this distinct lone pair of electrons on the nitrogen, okay? And again, we can think of them as deriving from ammonia. So primary amines have 1 hydrogen replaced by an R group or an alkyl group. Secondary amines have 2. Tertiary amines have 3. Okay, so tertiary amines have no hydrogen atoms on them. Okay. So naming amines, we need to use the amine suffix, which means it goes at the end. And the carbon chains are regarded as alkyl or aryl groups. Okay. So here we've got our methylamine. These are all examples of primary amines. Methyl, ethyl, and phenyl amines. Okay. And we have our naming of our secondary and tertiary amines, which is very similar to our primary amines, but slightly different nonetheless. So we've got our dimethylamine, trimethylamine, and ethyl-methylamine. And just a note on naming the amines, sometimes what we like to do is we like to put N at the beginning. So it would be like, you know, N-dimethyl amine, okay? And we wouldn't actually do it in this case, okay, because it's a very simple structure. But if we're getting into something which is a bit more complex, and we'll see this coming into some of the past paper questions that we'll cover, we might want to put this N at the beginning just to make sure that the people reading it know that the groups that we're talking about are attached to a nitrogen, okay? So the properties, we have this pyramidal shape, and this is due to the lone pair of electrons on the nitrogen atom, and we have a bond angle of 107 degrees, okay? And this is because this electron pair is kind of pushing these down and closer to each other, okay? So it's not 120 degrees, it's 107 degrees, okay? And again, these amines are polar molecules because of this electron pair. And they smell like rotten fish as well, okay? And then these properties, let me just get rid of all the ink on this slide. So the hydrogen bond with themselves, water and alcohols. And here we can see we've got a delta negative nitrogen group with this electron pair on, and it forms a hydrogen bond with a delta positive hydrogen group on another amine, another identical amine here, okay? And in terms of hydrogen bonding with themselves, this only goes for primary or secondary amines, okay? Tertiary amines can only hydrogen bond with water and alcohols. Okay, so it's probably worth noting that. Boiling points, they're wedged between alcohols and alkanes, okay? So they have greater boiling points than alkanes and lower boiling points than alcohols. And we can see this when we're looking at similarly sized molecules of alcohols, amines, and alkanes, okay? And in terms of their physical appearance, short-changed amines are gases at room temperature, and longer amines are volatile liquids, okay? So we also said that short primary amines are very soluble, and this is short primary amines being 1 to 4 carbons, are very soluble in both water and alcohols. And amines are still soluble in less polar solvents as well, because they are very polar molecules, okay? We also said that larger amines are less soluble, and amines that are attached to benzene rings are not soluble, because this benzene group here is extremely stable, and it actually, we'll talk about it later on, that actually reduces the polarity of this whole compound here, okay? Okay, so seeing as we've covered a few of these things already, it'll probably be a good idea for us to test ourselves on this, just to make sure that we're keeping up with our knowledge and making sure that we remember it, okay? So as I said at the beginning, from now on, we're not going to be using MS Teams quizzes anymore. What we'll use instead is a Slido, okay? And the way it is, and this way it's a bit more interactive, okay? So everyone will see, it'll be interacting together on an individual question all at once, okay? So it's good in terms of, just being a bit more engaging than sending you guys off to do a Microsoft Teams quiz, okay? So essentially what you need to do to use Slido is you need to either head to the website, or if you've got your phone and you've got the Slido app, you can type in this Slido code here, okay? So it's #K981, okay? So you need to go to the Slido website and you need to, I think there's a section saying participate as a guest or something on the website. It's a little green sort of button, and then you type in this #K981, okay? So I'm going to let you get onto that, and while you're doing that, I'm going to pull up the first question, okay? So hopefully you guys can see this. I'm actually going to have a look. Oh wow, okay, so yeah, some of you are already on it, which is really good. I'll give some of you a bit more time just to make sure that you're logged into that. So what is the name for this amine? And we have some people, 20 people in fact, have already answered this, okay? We'll just give you some time. I just want to make sure that the numbers on this one get relatively high, just so you guys all know. Of course, if you want to use a QR code, it is on the left there. You can scan that on your phone. I think you go into the camera app on iPhones, you can just kind of hold it over. And I think as well, you can use Snapchat, I believe, to scan a QR code, and that will take you to it. So I'll just let the numbers get a bit higher on this one before going on to the next question. Yeah, someone's just split it up a little bit. That's perfectly fine. So these questions are kind of, they're a bit more, they're just kind of going over what we've talked about already and hopefully making a bit more of an interactive session for all of you. I'll wait till it's got up to about, 45 answers. But again, we'll run the Q&A slightly differently, okay? We won't run it in the chat. So usually when I go over, when we finish the section, I usually ask about Q&As and ask you guys to ask some questions in the chat. I don't think we'll be doing that this time or from now on. What I'll do is I'll have a Slido slide, and it'll allow you to post one question if you have one, and we'll see them, and hopefully I can go through some of them as and when they come in, okay? So we're just about reaching 45, so I'm going to go ahead and go to the next question, okay? So just to make sure you guys know, yes, the answer for this question is methylamine, okay? So the next question is, what is the name of this amine? So we're going over our naming structures, okay? And hopefully you guys can see that in a bit of a bigger picture than what I can see. But yeah, have a go at naming that. Okay, so we have a couple of different answers here. We've got butylamine and we have tributylamine, okay? So I want you guys to think about which one could be correct in this instance. We have a few different answers, in fact. That's good. We will discuss which one is the correct one at the end. Again, hopefully you guys are finding this way a bit more interactive. You guys should be able to see on your screens which one is popping up more. Okay, that's interesting. We've got N-tributylamine. That's a very interesting way of putting it. Yeah. Tributylamine. I think that was just a typing error. Wow, we've got loads of different answers here. It's really, really good. Really, really good. I'll give a chance for a few more of you guys to input your answers. But it's really nice that we've got quite a lot of you, interacting with this. And hopefully you guys, obviously, I think we send out feedback forms. If you guys are really enjoying this, or if you prefer this method of interaction and quizzing, definitely let us know. We'll make sure to keep it on. Okay, so I think what we'll do is we'll discuss this question now. Okay, so the answer is tributylamine, okay? And if you guys can see, the biggest word that we've got here is tributylamine, which means most of you guys put tributylamine, okay? And that's really, really good. We have a few other answers here. We've got triethylamine. I think we've got a few spelling mistakes on tributylamine, but that's perfectly fine. And we have trimethylpropylamine, okay? So these are all very interesting answers, but essentially what we need to be looking at is we need to be looking at the R groups, okay? Are they the same? And how long are they? And in this case, they are the same, okay? And they should be 4 carbon longs. So that means they're butyl, okay? So they're not ethyl. Ethyl will be 2 carbon long. And trimethylpropylamine, that's a very interesting answer to this question, but all the groups are the same. Okay, all these groups should be the same, and that means it should just be tributyl amine. Now, one of you also put N-tributyl amine, and that's good. I understand that you're picking up on what we said with, starting it off with an N at the beginning, but not to critique you too hard, but the N at the beginning is usually when we use it when we're naming more complex amines, but I don't think you get penalized for that, okay? So it's really good that you're trying to put that N in. And then if possible, let's keep the tributyl amine as one word, okay? Just so they don't get too pernickety about it when they come to do marking schemes, okay? So let's move on to the next question. What type of amine is this, okay? And I can't exactly see how many of you, I don't think, are answering this for some reason. But I'll let you guys get your answers down, and then I'll talk over the correct answer. So here we have a nitrogen attached to 3 alkyl groups, okay? That's a bit of a clue. Although the alkyl groups in this case are not actually the same. They're not all the same as each other. So again, I'll wait till about 45 if you put your answers in. Okay, so the correct answer for this question is a tertiary amine, okay? And this is because we've got it attached to 3 alkyl or R groups, okay? And there's no hydrogens present on this nitrogen, which is, also again a giveaway, the fact that this is a tertiary amine. So tertiary is attached to 3 alkyl groups or R groups. Secondary is attached to 2 and has 1 hydrogen. And primary is attached to 1 alkyl group or R group, and it has 2 hydrogens, okay? So in this case, this is a tertiary amine. And it seems like 91% of you got that one right. That's really, really good. In fact, that's very good, 91% of you. And, hopefully I've explained it enough so that those of you that didn't pick that answer as your first choice, hopefully you guys will understand why that is the correct answer, okay? So then, the next question is, can tertiary amines H-bond between themselves? Okay. Let's have a look at some of you answering this one. You guys are getting really good, actually, at getting these answers in quickly. It seems like quite a lot of you are interacting with this. So hopefully you find this a bit more enjoyable than, just the Microsoft Teams quizzes and me going over the answers at the end of it. Because this way you can get a bit more feedback and see what everyone else is thinking. And of course, if all of you get something wrong, then it allows me to go back and cover it as well. Okay, I'll give you a few more seconds to get that one. Okay. I'll give you 10 more seconds, and then we'll move on to find the answer out. Again, if you are finding this difficult, don't worry. This is this is your first time looking at this stuff, so don't worry yourself at all. If you don't get them right, we will summarize and go over things again. Okay. So, looking at the answer is no. Okay. And 65% of you guys got this right, okay? Or 67% now. So essentially the reason why tertiary amines cannot H-bond between themselves is because tertiary amines don't have a hydrogen left on the nitrogen atom, okay? There's no hydrogen to bond with on the nitrogen atom, okay? So although the nitrogen is still delta negative because it has that electron pair, that lone pair, it still can't bond onto another tertiary amine because there's no hydrogen on it, so there's no H bonding. They can, however, H bond with ethanols or alcohols and water, okay, because those have hydrogens on them, okay? But because tertiary amines do not have hydrogens left on them, they have 3 alkyl or aryl groups, or R groups. This means that tertiary amines cannot H bond with themselves, okay? So, good. So we've got about 73 at the end. Okay, good. So, let's have a look at this other question. Are tertiary amines soluble in water? And I might have given this away in the last question. Okay, I might have just given this away. So I'll give you, a minute just to get your answers in. And of course, if you do attend the other classes as well, so we've got year 13 biology, I believe. We are again using Slido in those classes, I think, from now onwards. So again, if you find this really nice and interactive, and it kind of, keeps you on your feet a little bit more, I think. So if you're finding it good and interactive, then yeah, we do have more of it, and we're incorporating it from now on. Of course, your feedback would obviously be really, really useful, and I think we do send feedback forms every now and then throughout the session. Okay. So we have 40 responses. I'll just let a few more of you get your answers in. It's good. You guys are getting really quick at answering these questions, which is quite an encouraging sign, to be quite honest. Shows that you've got confidence in it, which is really good. Okay, so let's find out the answer to this question. So, are tertiary amines soluble in water? And the answer is yes, tertiary amines are still soluble in water. Okay, and as I talked about on the last slide, I said that tertiary amines can still H bond with water because they have hydrogen atoms. Okay, they have hydrogen atoms. So because if water has a hydrogen atom, the tertiary amine still has that electron, that lone pair electrons on the nitrogen atom. Okay, so that means there can still be a H bonding between the water, and that means that they're still soluble in water. But again, we still need to make sure that tertiary amine is relatively small in carbon chain length, because if the smaller the carbon chain length, the more soluble it is in the water. Okay, because the smaller the molecule is in general. Okay, so for those of you that were confused, hopefully I explained that again a little bit better. But of course, we can always go over at the end once we've covered this first section. So great. So we've done our first Slido and we've done our first section in this, this first teaching block. So it's really good to see you guys interacting with this new way of doing quizzes and questions, and hopefully you guys like it. But for now, what we're going to do is we're going to make a start on the second little section in our amines, okay? And this second section is making primary amines, okay? So there's 2 methods that we should really know about when we want to make amines, okay? And the first is making amines through using alkanes, nitrile groups, and their reduction, okay? And the second method, which we'll go over in a few minutes after a few slides, is by making amines using ammonia, okay? So let's go over making primary amines by using haloalkanes, nitriles, and reducing them first, because I think it's a bit more of a simple mechanism for you to understand. Okay, so firstly, what we need is a nitrile group. Okay, and the functional nitrile group is C triple bond N. Okay, you might have seen this before. If not, and this is your first time seeing it, this is what we have. So it's C triple bond N. Okay, and the first step. Oh, also, by the way, this is also known as a cyanide ion. Okay, It might be a little confusing if you think this is, if someone says nitrile, you think of this, and then someone might say cyanide. It means the same thing essentially. Okay. So step one is a nucleophilic substitution reaction. Okay. It's nucleophilic substitution. So we've got the haloalkane and the cyanide in aqueous ethanol. Okay. So this is one of the conditions that we need. Okay. For this reaction to take place, we need aqueous ethanol. Okay. And the first step, the cyanide ion replaces the halide ion on the alkene, okay? So this halide, HA, means any halogen, essentially. So we'll have, our haloalkane, our cyanide group, and essentially there's a nucleophilic substitution reaction that occurs, and we get the formation of this alkane and our cyanide group. And we displace this halogen, and that goes off in solution away from this reaction. Okay. So the key thing for us to remember at this step is that the conditions that we need are we need aqueous ethanol present. Okay. So the second step in this reaction is the reduction of the nitrile group. So we saw that we had the addition of this nitrile group here. Okay, or the substitution of this nitrile group onto the alkane. Okay. So the second step in creating a primary amine, okay, with the reduction of nitriles, this method here called the reduction of nitriles, is reducing the nitrile, okay? And this we use catalytic hydrogenation for this step, okay? So you have our nitrile, our alkane with our nitrile group on, or a nitrile, and then we have hydrogen, okay? And then we put it under a catalyst and we get the production of a primary amine, okay? And it's a primary amine because we have two hydrogens attached to our nitrogen and, one alkyl group or, alkyl group attached to the nitrogen as well. Okay, so that's our formation of a primary amine. And the catalyst that we'd use in this situation is nickel. Okay, and this would be under raised temperature, increased temp, and increased pressure. Okay. But you don't have to remember exact numbers, okay? Because it depends on the individual catalyst that you use for any reduction of nitrile reaction, okay? So just to summarize essentially this reaction, let me get rid of all these drawings. So we have step one of making a primary amine through the reduction of nitriles is a nucleophilic substitution reaction, okay? In an aqueous ethanol condition, okay, so it needs to be an aqueous ethanol condition, and we have a haloalkane and a cyanide ion, which is our C triple bond N, and we have a nucleophilic substitution reaction that displaces this halide group and forms a nitrile group. Okay. Then we have the reduction of the nitrile through catalytic hydrogenation, or the addition of hydrogen. So we have our nitrile and we have our hydrogen. And under a catalyst, a metal catalyst or a nickel catalyst, we get the formation of a primary amine. And it's a primary amine because we have two hydrogens and one R group, okay, attached to the nitrogen, okay? And again, this would be under raised temperature and pressurized conditions, but you don't need to remember any specific pressures or temperatures because it depends on the catalyst that you use, okay? So the second method of forming amines, and in fact, forming any amine, is from ammonia. So if you actually look closely, the title of these slides are making primary amines, okay? Because you can only make primary amines through the reduction of nitriles, okay? If we want to make primary, secondary, tertiary, and potentially quaternary ions, ammonium ions, we need to make them through the use of ammonia, okay? So again, this is a nucleophilic substitution reaction, okay? And it forms 4 different products, as I said, okay? So due to the nucleophilic nature of amines, okay? So primary amines will form when ammonia undergoes nucleophilic substitution reactions with haloalkanes, again. So here we have, a reaction equation. So we have ammonia. Remember, ammonia is NH3, ammonium is NH4. And we have a haloalkane again, okay? We get a nucleophilic substitution reaction, very similar to the last way of forming amines. So we get a nucleophilic substitution reaction, we displace this chloride ion, and we get the formation of this primary, we get the formation of this, this alkane with an ammonia ion attached to it, okay? Or ammonia attached to it. And notice that this is a positive, okay? Notice that it's positive because we still have this third hydrogen attached, okay? So rather than a primary amine being 2 hydrogens, this has got 3 hydrogens, so it's still positive. So what do we do to resolve that? Well, we have a second ammonia group attached to this, or attack this positive hydrogen, okay? And we get the formation of our primary amine and our NH4 plus our ammonia ion, okay? So this is essentially what we've got here. We've got this nucleophilic substitution reaction split into two steps. So we've got the addition, the substitution of this chloride ion here. So essentially we have this electron pair attacking this delta positive carbon, okay? So it attacks this delta positive carbon, and this forces the electron to be withdrawn onto our chloride group, and this becomes a leaving group, okay? And then we have the addition of this ammonia, and we get the formation of our product, our intermediary product, okay? Which is this, the ammonia added onto our hydrocarbon, okay? In the second step, where we get, the rectification of this positive charge, essentially, is where we have another ammonia coming in. Again, it has its double, its electron pair, its lone electron pair. So it acts as a nucleophile again, and it attacks this delta positive hydrogen group, okay? Oops. And then the electron goes onto, this is not delta positive, in fact, sorry, the nitrogen is delta positive, okay? And the electron is then withdrawn onto the nitrogen to equalize this charge, and then we get the formation of a primary amine and an ammonium ion, okay? So that is the nucleophilic substitution reaction. So it's got 2 steps to it. Essentially, we have the substitution side of things, and then we have the rectification side of things, making sure that it is the nitrogen is not positively charged in terms of electrons, okay? So we have had this, so the primary amine is a nucleophile, and so we've had the formation of a primary amine, okay? And now we can actually get the formation of a secondary amine, and it's very, very similar to the last reaction steps that we've had, okay? So the primary amine is also a nucleophile, okay? Because you said that these nitrogen groups, they have their lone pair of electrons on them, okay? So it can also act as a nucleophile, and it will react with another haloalkane to produce a secondary amine, okay? So here we've got an equation. We have a haloalkane, we have a primary amine here, and we get the formation of this this intermediary, which is positively charged. Again, very similar to our last step of things. And we have our leaving group, which is our Cl- or our halogen group, okay? And again, we need to make sure that this is correctly charged. So we have this intermediary here reacting with another ammonia, and we get the formation of a secondary amine here and another ammonium ion, okay? And remember, a secondary amine has 1 hydrogen attached to it, okay? 1 hydrogen attached to the nitrogen, okay? And then, we've said the R groups are alkyl groups, okay? And again, this can happen another time, okay? And this time we have the formation of a tertiary amine. So essentially the same reaction that's taking place again and again and again, okay? So we have, our haloalkane reacting with our secondary amine, in this case, forming an intermediate and a chloride ion, or whichever halide you're going for. And then we get our intermediate reacting with an ammonia again, and we get the formation of a tertiary amine and the formation of an ammonium ion, okay? And this reaction can occur one more time to form our quaternary ammonium salts, okay? So I know that we've only talked about primary, secondary, tertiary amines. That's correct up until now. We can also get this quaternary ammonium salt, okay? And this is where we have our tertiary amine reacting with a haloalkane, and we're forming this intermediary, well, what would look like an intermediary in the last steps, okay, but was actually a quaternary ammonium salt in this final step, okay? So when we've got a tertiary amine reacting with a haloalkane, we get the formation of this quaternary ammonium salt, okay? And it's positively charged, okay? It's positively charged. So what we're going to do now is we're going to go over some more Slidos, okay? So if you guys log back onto Slido, you know, go on the hashtag K981. We've got a few more questions here. So which method allows for easy formation of quaternary ammonium salts, okay? So you've got two options here, two options. The first option is making amines from ammonia, and the second option is making amines from nitriles, then reducing them, okay? It's probably worthwhile you guys keeping Slido up, just because we're going to be going through things quite frequently on Slido, just making sure that you guys understand things, okay? So I'll give you some time to answer that question. So essentially, if I was to simplify this down, it would be, so which method allows the easy formation of quaternary ammonium salts, okay? The first step, the first method, which is, you know, our cyanide group, or our, the first answer here is the one we just went over, and the second answer here is making amines from our cyanide group, okay? So which one is going to be the one that allows us to easily form quaternary ammonium salts, okay? So either making amines from ammonia, which is what we just covered, or making amines from nitriles and reducing them. Which one do you think is going to be easier to form quaternary ammonium salts, or even form quaternary ammonium salts overall, okay? Which one do you think? I'll give a few more of you a chance to answer this question. Okay, I'll wait another 10, 15 seconds. And if you don't know the answer, don't worry about it at all, okay? We can always go over it. So give me another 5 seconds, and then we'll go over the question. So if you don't know, don't worry. We'll cover this. We'll cover the answer to this question, okay? Okay. Great. 77% of you got this one right. And I'm actually really impressed by that, because both of those are, you know, kind of complex mechanisms. And I understand if you didn't quite, you know, grasp it initially. But the correct answer is making amines from ammonia, okay? And that's because making amines from ammonia allows us to get these subsequent reactions with, you know, ammonia and haloalkanes again and again and again. Pardon me. That allows us to form not only primary amines, but secondary amines, tertiary amines, and quaternary ammonium salts. Making amines from nitriles and then reducing them only allows us to form primary amines, okay? Because we don't have ammonium, and we don't have any more, well, yeah, we don't have ammonium, and that doesn't allow us to get these subsequent reactions taking place, okay? So that's really good. Okay, so now 89% of you got that right. Okay, so moving on to the second question. What are the required conditions for the formation of amines from ammonia? And in fact, I haven't covered this, so let me go back and talk over that quickly. Okay. So in terms of making amines from ammonia, we actually need a few different conditions, okay? And it's actually similar to our past the reduction of nitriles, okay? So We need alcoholic conditions. Okay, so we need to include aqueous ethanol. So aqueous, oops. And we need to heat this, well, we need heat, okay, to allow this reaction to occur. And we also need to heat it under reflux, okay? And this is so that, you know, it's an enclosed container. So if some of you don't know what reflux looks like, it's kind of like a flask with a stopper, and you heat it with an electric heater, okay? And you have our reaction solution here, okay? And essentially, you know, because it's stopped, like nothing can escape at the top, we have any gases that go up will just condense and drop back down again, and we have the continuation of a reaction occurring in here, okay? And we'll get different stages of reaction. So we'll get, in this case, we'll get primary, secondary, tertiary, and quaternary ammonium salts in this reaction liquid here, okay? And of course, the longer you react it, the higher the concentration of the latter stages or the latter products, okay? So we need to have aqueous ethanol solution, we need to have heat, and we need to heat it under reflux, okay, in an enclosed container, okay? So having just gone over that, let's go back to that question so you guys can answer it, okay? So what are the required conditions for the formation of amines from ammonia? So essentially what we just covered then, okay? I think you should be able to select multiple answers for this one. If not, then I think I must have made a little mistake, but don't worry, we will go over it. Essentially, what are the required conditions for formation of amines from ammonia? And it's just what I said just then, okay? So if you don't know it, don't worry, because I did realize I hadn't actually said it beforehand, but I will say it again after we've got the answers to this question back. And again, if you don't know the answer to any of these questions, don't worry at all. This might be some of your first times going through this, and it's perfectly acceptable to be making mistakes at this stage of things. You know, we want to be making mistakes now, so we learn from them. And when it comes to exam time, you know, we're getting the right answers. There's no point, you know, there's no point not understanding where, you know, you don't know things, you don't know topics, because, you know, if you make mistakes now, at least you know where you've made the mistakes and you can correct those going into the future. And hopefully that means that it'll translate into good marks. Okay, I know I made loads and loads and loads of mistakes whenever I've learned a new topic, and that way I just got to know exactly where I was going wrong and how I could fix that. Okay, so it's perfectly understandable if you're not getting, let's say in this question, all the required conditions, partly because I did just go over them because I forgot to go over them again. So that's perfectly fine. But, you know, other questions, if you don't quite get it right, don't worry. Just write it down on a piece of paper. Maybe you can come back to that, or maybe we'll go back over it in a summary. OK, so great. 86% of you got reflux. 78% of you have got heat. Sorry, 78% of you got aqueous ethanol, and 76% of you got heat. Okay, so those are the required conditions for formation of amines from ammonia. So heat, reflux, and ethanol. Okay, a metal catalyst is something that we use in the reduction of amines. Sorry, reduction of nitriles to form primary amines, and hydrogen will be required in that reduction of nitriles to form a primary amine. Okay, so that's the reason why we have these answers here. So moving on to the next question, what type of catalyst is needed to reduce nitriles in the formation of primary amines from haloalkanes and nitriles? Okay, so it's actually semi just what I just said before, so I might have given you a little bit of a clue, but here are the answers. So we've got potential answers here. We've got acidic, basic, metal, or porous pot. Okay, so I'll give you another few seconds to answer that. I'll wait till about 35 of you, 40 of you have put your answers in. Yes, we've got 20 people. Okay, I'll give you another 10 or so seconds. Okay, so the answer to this question is metal. Okay, and it's really good that 64% of you guys got that one correct. So the type of catalyst that we need to reduce nitriles in the formation of amines from haloalkanes and nitriles is a metal catalyst. Okay, and that's that first reaction that we covered. Okay, the formation of primary amines from that cyanide ion. Okay, and the reason why it's not acidic is that we don't need an acidic. I think what some of you guys might be mistaking acidic and basic for is the ethanoic conditions. Okay, we need ethanoic conditions. Okay, but we also need our metal ion. Okay, we need our metal catalyst. Okay, that's the actual catalyst that we need. Okay, so you could also, well, we talked about nickel. That's a specific metal catalyst. First question, all you need to say was metal. I think there are a few other metal catalysts that you could use, but generally we use nickel. Okay, so then let's move on to more properties of amines. Okay, so amines, so actually we'll talk about basic reactions. Okay, so amines are Bronsted-Lowry bases. Okay, and don't worry if you don't know what that is. If you do, really well done. Bronsted-Lowry bases means that they are they are proton acceptors. Okay, so they accept protons. So that is exactly what we've got here. So amines will react with acids to form salts, and in this case, it will form quaternary ammonium salts. Okay, so here's an example. So here we've got our primary amine, in fact, here, and we have HCl, which is our hydrochloric acid. Okay, and we can see here our lone pair on our nitrogen actually attacks this hydrogen here, and this allows the chlorine to withdraw the electron from their bond onto itself. We've got the formation of a chloride ion, and we have a positive ammonium salt here. Okay, so sorry, I said quaternary ammonium salt, I just meant an ammonium salt. Okay, so we have a positive ammonium salt here. Okay, and we can see the equation for this reaction down here. So we have H plus Cl minus. Essentially, this is because strong acids dissociate themselves, so almost entirely dissociate themselves. So we have, and dissociation is the sort of the breaking up of the acid into its constituent ions. So that's H plus and Cl minus, plus our primary amine goes to form an ammonium salt plus chloride ions, okay, in aqueous solution. So these ions will crystallize on evaporation of the solution. So if we evaporate off, these chloride ions and everything, or if we evaporate off the solution, we'll get these really nice crystal structures. And the purer the solution, or the purer the reaction, essentially, the less impurities there are, the nicer and the bigger the crystals will be. Okay. So let's move on to another basic reaction. So we said that phenol amine is insoluble, okay? And we said it's insoluble due to this large, stable benzene ring that it's attached to, okay? Well, it actually will dissolve in excess hydrochloric acid, okay? And it will form a soluble salt, okay? And we can see this reaction here, okay? So you've got our hydrochloric acid, which has been dissociated into solution, and we have our phenol amine. And we get the formation of this, this ammonium salt here, okay, which is actually soluble. Okay, this is a soluble salt because we've got this positive charge here. Okay, it's polar. We get, plus Cl minus. But amines are weak bases. Okay, so a stronger base, for example, a hydroxide, okay, will displace the amine and form another salt. Okay, so the phenol amine will become insoluble again because it will be displaced, and it'll become phenylamine once more, and it will become insoluble again. Okay, so this is one area where we can get this phenylamine, which is generally a very insoluble compound, to become a soluble form, which is if we form a soluble salt, it can become soluble in excess hydrochloric acid. Okay, but then again, if we have a stronger base, like a hydroxide, then it will displace it and we'll get the formation of phenylamine, which is insoluble again. Okay, so we just said that amines are weak bases. Okay, and let's talk a bit more about their basic strength. Okay, so a base's strength depends on how readily it will accept a proton. Okay, if we're talking about Bronsted-Lowry theory, that is, of course. Okay, so amines are stronger bases than ammonia. Okay, and this is due to something called the inductive effect. Okay, so the inductive effect is the unequal sharing of bonded electrons. Okay, and this is what we've got here in this diagram here. Okay, so the inductive effect is electrons moving towards the nitrogen. Okay, so essentially we have this alkyl group here. Okay, and this alkyl group, because it's methyl, it will push these electrons, okay, over. So alkyl groups are electron pushing groups. Okay, and it will push the electrons and form a more delta negative force on the nitrogen. Okay, so essentially we have this inductive effect. It makes the nitrogen a lot more electronegative, and that means it becomes a lot more polar, and therefore it will become a stronger base. Okay, so the inductive effect is stronger in secondary and tertiary amines. Okay, however, tertiary amines are weaker bases due to solubility. Okay, so we can see here that we've got a secondary amine here, and we've got two. These two alkyl groups are both pushing this electronegativity onto this nitrogen. Okay, so it's quite, it'll be obvious as to the fact that this is a stronger base because you've got a higher inductive effect. Okay, but we said that tertiary amines are weaker bases because of their solubility, so they might have more inductive effect, okay, than secondary and primary amines, but because they are less soluble, that means they are weaker bases. Okay, so let's talk about this phenol group, or this benzene group. Okay, so aromatic amines are weaker bases than ammonia. Okay, and this is because the induction effect actually happens in the opposite direction. So this is because this benzene group actually it takes away, it takes away the pair of electrons. Okay, so a lone pair of electrons overlaps with the delocalized electrons in the benzene ring. Okay, and so attracts the lone pair towards the benzene ring. So this actually makes it less delta negative. Okay, it makes the nitrogen less delta negative because the electron cloud will be more skewed over to this direction here. Okay, so this makes it less polar, and that means it makes it a reduced strength base. Okay, so essentially we have this little diagram here. So we have basicity, or the strength of our base. We have ammonia in the middle. Okay, and then we have our primary, secondary, and tertiary amines on this side of things. Okay, and then we have a phenol amine on this side of things. Okay, and of course this is, our phenol amine is a less strong base than ammonia because the benzene ring withdraws the electron. Okay, or it takes the electron negativity closer towards it, which means that it's less polar, and that means it's less accepting of a proton. And then, on our other side of things, we've got our primary, secondary, and tertiary amines, and these have a positive inductive effect onto the nitrogen, which means that this becomes more polar and more accepting of a proton. But just to make sure that you guys know this, the tertiary amines are not as strong bases because they're not as soluble. Okay, that's the key thing with them. So although they have a higher inductive effect, tertiary amines are not stronger bases necessarily because they're not as soluble. Okay, so that's essentially just a summary. You could take a picture of this. In fact, probably what I'd do is I'd take a picture of this. So I'm just going to erase the ink. Give you a few seconds if you've got a phone to take a picture of it, or a screenshot by clicking print screen on your computer. And this is just a summary, really nice summary of base strength. Okay. So let's talk about a bit of the uses of amines. Okay, so you need to know a few of the uses. So one of the uses of amines is the use in nylon. Okay, and essentially it's a polymer or a plastic that's used a lot in clothing. Okay, so your coat might have nylon, your school blazer might have nylon. It's used a lot in clothing. Okay, and it's quite durable. We also have polyurethane. Okay, and that's another polymer which is flexible foam used in furniture and cushioning. So something like, if you cut your sofa open, you'd probably see this polyurethane, which is kind of like this, sort of yellowy or whitish foam. It's really nice and comfortable. Okay. We also have the use of amines in dyes, and we also have, more medically speaking, the use of amines in drugs. Okay. So let's have a look at the use of amines in drugs in a bit more detail, seeing as you guys do want to become doctors, or at least want to go into the sciences. Okay. So you've got sulfonamide, okay, sorry, sulfanilamide, okay, a very difficult drug to pronounce, okay. So it was a first antibacterial drug, okay, and it was observed that some dyes essentially kill bacteria because, of course, we have these dyes that use amines, okay, and essentially what they did is they observed that some of these dyes actually killed the bacteria, okay? And it works by preventing the bacteria from making folic acid, okay? And they need the folic acid to replicate. So if they stop them from making the folic acid, then there is no replication, and therefore it's antibacterial, okay? And it's a similar shaped molecule to one of the reactants bacteria need to make folic acid, okay? So essentially it inhibits this whole process because it's a very similarly shaped molecule. Okay, so it's inhibition or competitive inhibition. Okay, so then that's one example of a drug that uses amines. Okay, and of course, here we have the amine groups attached here. So we've got some other drugs that are used. So we have fluvoxamine, which is a selective serotonin, or well, an SSRI. Okay, this is what we call these SSRIs. Selective serotonin reuptake inhibitors for OCD. We also use SSRIs as antidepressants or anti-anxiety drugs. They're quite common. I think they're probably one of the most common classifications or types of drugs that are prescribed nowadays. We have amphetamine, which is a central nervous system stimulant, and a sympathogenic agent for ADHD. Okay, so amphetamine, it actually has been used in a lot of drug disorder. So a lot of people have drug addictions to amphetamines. If you think of stuff like crystal meth, it's highly addictive, but it does have its clinical usages in something like ADHD. Okay, and we have Esmolol, which is a cardioselective beta adrenergic blocker for short-term control of heart rate and various types of tachycardia. So tachycardia is where the heart rate is increased, by a lot. So our normal heart rate is anywhere from 60 to 80 or 90 beats per minute. Okay, tachycardia would be something like 120 beats per minute. And essentially, this Esmolol allows the heart to reduce, or it causes the heart to reduce its contraction rate, okay, or its beats per minute, and that's used in when we're trying to control someone's heart rate, let's say in heart failure, okay. And we've got carbidopa, which is a decarboxylase inhibitor used to reduce Parkinson's disease symptoms. And essentially, this works by, we give Parkinson's disease sufferers, or those with Parkinson's disease, dopa, okay, or L-dopa, and essentially that's dopamine. So it goes into the brain, or we give them L-dopa, which is sort of like the precursor to dopamine. It goes into the brain, and it helps the brain. The brain converts it into dopamine, but similarly, it goes to everywhere else in the body. And essentially, what we need to do is we need to stop the conversion of the dopamine elsewhere in the body, because if we get the L-dopa being converted into dopamine, then it causes things like shakes and tremors, because it is a neurochemical essentially. So we use carbidopa to stop the peripheral conversion of L-dopa, which is used to treat Parkinson's disease, into dopamine. Okay, and that stops nasty side effects for about a few years. Okay, but those are just sort of, as a medical student, I know some of those things because I've studied those things. You're not expected to know those in great detail for your exams. Okay, but that was just, I thought some of you might find that a little bit interesting. So in summary, we've got amines have nitrogen in them. Primary amines are ones with just one R group and 2 hydrogens. Secondary amines have 2 R groups and 1 hydrogen. And tertiary amines have 3 R groups and no hydrogens. Okay, so this is probably the most key thing that you guys need to take away from this section. So if you were to forget everything, you need to make sure that you can classify between primary amines or amides, secondary and tertiary. Okay, they have suffixes. So the suffix is amide, and prefix is the R group, and they form a pyramidal shape with 107 degrees bond angle, and they are polar molecules, and they can form hydrogen bonds. Okay, so they have higher boiling points than alkanes, but lower boiling points than alcohols. They're small. The smaller the amine is, the more soluble it is, and the larger the amine is, the less soluble it is. So phenol amines are not soluble, and that's because of that benzene ring, and that's super stable, and it reduces the polarity or the ability of the amine to be soluble, so they're not soluble, apart from in excessive HCl solution. We have primary amines can be made by the reduction of nitriles, which is that cyanide group, and the hydrogenation using a metal or nickel catalyst in ethanoic solutions. All types of amines can be made from ammonia and a haloalkane. So we get that reflux, and we get the, let me just grab a tissue. And we get the formation of primary, secondary, tertiary, and quaternary ammonium salts. Okay. Amines can act as Bronsted-Lowry bases. That means they are proton acceptors. And we have phenol amine. In terms of base strength, we have ethyl amine, okay, ammonia, and phenol amine. Okay, so we've got our primary, secondary, tertiary amines here, ammonia, which is the medium ground, and phenol amine. And this is all due to the inductive effect, which is the uneven sharing of bonded electrons. Okay, and it makes straight chain amines more basic, and amines with benzene rings less basic. Okay, so then before we have our 5-minute break and go over a few past paper questions, we've got a few more Slido questions. Okay, got a few more of these, and then we'll have a little break, and then we'll go over some past paper questions. Okay, so then again, if you want to join the quiz, should have a question there. I think you guys should be ranked at this point. So I'll wait till a few of you guys have joined. I think you can input your name. And that way, essentially what happens is we've got a few questions here, and at the end of it, we'll have a ranking, and it shows which one of you guys have got successively the questions correct. Okay, it's a bit like Kahoot, but just more integrated into the PowerPoint. Okay. Always good to see someone else who's called Matt. I'll let a few more of you guys join. Obviously, it's really good to get involved in this sort of thing because it kind of just allows you to test your knowledge a little bit more. Okay. So I'll wait till a few of you guys have done that. I'll give you 10 or 15 more seconds to join the quiz. And don't worry, if you don't join this one, we do have some more quizzes coming up later on, okay? Okay, so I think what we'll do is we'll start the quiz, okay? So the first one is, what type of amine is benzanoamine or phenol amine, okay? Got 10 more seconds to answer this question. So, these are quite quick fire questions, okay? Okay, primary. Okay, good. The answer is primary. Leaderboard is T, who got it in 6 seconds, okay? That's good. Okay, so what bond angle is present in the pyramidal shape of amines? Try and get these as quick as you can, as best as you can. 10 seconds left. Okay, so have a look. So lots of you said 107 degrees. The correct answer is 107 degrees. It's not 120 because we have that spare pair of electrons at the top of the nitrogen, which kind of pushes everything down. It kind of forces everything together, okay? Repels everything else. So at the top of our leaderboard is Maddie, who's overtaken whoever was last. I think whoever it was top last, I think it was T. And Maddie got it in 12 seconds, so well done, Maddie. Let's see if you can continue or whether someone else will take your spot. So which method would you use to create a secondary amine? So either reduction of nitriles, which is the first thing we covered, or nucleophilic substitution using ammonia. 10 seconds left. Let's see who gets this one correct. So most of you have said nucleophilic substitution using ammonia, and that is the correct answer. So nucleophilic substitution of ammonia allows us to create primary, secondary, and tertiary amines, and also the formation of quaternary ammonium salts. Okay, so well done, MS. You got that in 17 seconds. Okay. So what's the conditions for preparation of amines using ammonia? Okay, so we've had this question before, essentially. So if you can remember it, you should be able to get this question correct. Let's have a look at what you guys think. Okay, so there are 3 answers to this question. It's heat, reflux, and aqueous ethanol. Okay, so let's see who's on top. JJ is on top. Wow, we're really shifting around who's on top of the leaderboard at this point. So well done. It took you guys, well, it took JJ 25 seconds to do that. That's pretty quick. Okay. So what is the inductive effect? The equal sharing of unbonded electrons, the unequal sharing of unbonded electrons, the equal sharing of bonded electrons, or the unequal sharing of bonded electrons. Okay, this is quite a mean question because there's a lot of things that look the same. Let's have a look at what people have said. So most of you have said either the unequal sharing of unbonded electrons or the unequal sharing of bonded electrons. So which one is correct? It is the latter. So it's the unequal sharing of bonded electrons. So 62% of you got that right. So these are really encouraging marks, actually. So the winner for this part of the quiz, we have got multiple quizzes coming up later, is MS. So you managed to reclaim the title, I believe, and that's really good. So the hardest question, it seems, was what is the inductive effect? And that really was a tough question, I have to say. It was me making you read through all four of those different, very similar potential answers. Okay, so what we're going to do now is, I think it probably wouldn't be great of us to start exam questions and then just like finish halfway, just have a break halfway through them. So I'll let you guys have a 5-minute break at this point in time. So if you come back at 11:30, we'll have our 5-minute breaks, 5 minutes earlier. If you come back at 11:30, we'll start some past paper questions, and we'll then move on to our second topic for today. So I'll see you back at 11:30. Okay, so hopefully you guys can hear me again. I think what we're going to do is we're going to finish. So we've finished our break. So hopefully you guys are back. Yeah, so ideally you guys would have stretched, had some water, just so it's a bit easy to concentrate. I definitely filled my water up again. I'm actually going to take a sip of that. So then, what we're going to do now is we're going to go over some more past paper questions, and that way, we get to put into practice what we've just learned in the first section. And by the looks of it, especially with that quiz, it does look like a lot of you guys have taken on board quite a lot of information. And obviously, it's not going to be perfect and taking on board everything, but it definitely looks like you guys have understood quite a lot of the concepts and the topics that we've taught today, or taught so far, in fact. So what we're going to do is we're going to move on to our exam questions. Okay, so our first question here is question 1A. So which one of the following is not a correct general formula for the non-cyclic compounds listed? Okay, so essentially we have a bunch of general formulas here, and you kind of have to go through each one of them and sort of see whether these are correct or not. Okay, so the way I would do it personally is I'd just come up with an example, a small example of each individual one, okay, and I'd just test it, okay, and see whether it fits the characteristic. And if you did that, what you find is for aldehydes, let's get a formula such as butanol, okay. Remember, aldehydes have a functional group of COH, okay, which is something like COH, okay. So butanol is an aldehyde, okay, and it has a formula of C4H8O, okay. And if we have a look at the general formula here, this doesn't actually match up, okay. It says CnH2n plus 1O, okay. So this doesn't match up to our formula here, which is, it would be CnH2nO, okay. So the correct answer for this one, or the which of the following is not a correct general formula, would be B, okay? So moving on to B, which compound is the strongest base, okay? So you have ammonia, ammonium chloride, methylamine, or phenol amine, okay? So then, if we think about this, we had on slide 36, we had a summarization of the inductive effect. So here we're looking at the inductive effect. So we had our NH3 in the middle in terms of our basicity or base strength. And then we had our, our primary, secondary, tertiary amines on this side, okay? Oops. And then we had our phenol, amines on the left, which weren't as strong bases. So if you have a look at this, ammonia is the middle strength, okay? So it's this point here. Ammonium chloride, well, that would be sort of our quaternary ammonium salt, okay? So that would be on this side of things, but again, it's not very soluble, okay? So that's probably not the right answer, okay? Then we have methylamine, okay? So that's a primary amine, okay? And that is, again, on the right-hand side of things, okay? Then we have phenol amine, which is on the left-hand side of things. So by all accounts, it looks like it is C, okay? So it looks like methylamine is the correct answer here. Okay, then, so question C is aqueous solutions of ammonia, ethyl amine, and phenol amine are prepared. Each solution has the same concentration. Which is the correct order for pH values of these solutions? So again, we need to consult our summary of base strength and the type of amine it is. So we've got phenol amines, ammonia, and primary, secondary, tertiary. Okay, so we've got ammonia, which is in the middle, ethyl amine, which is a primary amine, so that's currently looking like the strongest, and we've got phenol amine, which is looking like the weakest. Okay, so weak, strong, middle. So now we need to put this in order of pH values. Okay, so this means it's going to have a higher pH value. This one's going to have a lower pH value. This is going to have something in the middle. Okay, so the correct answer should be C. Okay, so you've got ethylamine being the highest or the strongest, then followed by ammonia, then followed by phenol amine. So we're going to go with C. And if we have a look at the answers, yes, those are all correct. Okay. So then, this exam question is exam question number 2. Okay, and this is talking about infrared spectra. And don't worry if you haven't covered this before. I think it's slightly mean of me to add this question in because I know a lot of you haven't covered infrared spectra before. But let's just talk through this question. So the infrared spectra A, B, and C are those of primary amines, of a primary amine, a tertiary amine, and a nitrile, but not necessarily in that order. Okay, so give the letter of each compound in the correct box. So what I'm going to do is I'm just going to fill this one in because we haven't actually taught that. And I think for some of you it might not necessarily be in your spec either. Okay, and essentially what we need to do is, if you were to do this question, you'd be looking at signature regions. Okay, so that's what you'd be looking at. You'd be looking at signature regions and seeing which match up to which. Okay, so the actual answer to this question would be C, B, A. But let's move on to part B. That is a question that we can do. Okay, so there are 3 secondary amines that contain 4 carbon atoms per molecule. Draw the skeletal formula for these 3 secondary amines. Okay, so 3 secondary amines that contain 4 carbon atoms per molecule. So this means that nitrogen group has to be connected to 1 hydrogen and 2 carbons, or alkyl groups. Okay, so if we've got 4 carbon atoms per molecule, there are and it needs to be connected to 2 alkyl groups. There are 3 secondary amines. Okay, so I want to give you guys a minute just to think about which ones they would be, and then what I'll do is I'll flash them on the screen and I'll explain them through. So I'll give you guys just 1 minute just to think about that. And again, this question is actually asking for skeletal formula. Okay, so it's not our standard structural formula, which is us just drawing them out with the bonds and everything. This is our skeletal formula, so it's much more like this. Okay, so that's the sort of thing that we're looking for. And if it was to nitrogen, it would be like this. And instead, so each one of these points represents a carbon, but because it's a nitrogen, we just draw it like that. Okay, and then it'd be something like that. Okay, so I've given you about enough time. Don't worry if you don't have all 3 of these written down, but let's flash these in. So we have these here. So essentially we've got 3 of them available, and you can either draw them like this, which is how I'd probably draw them, which is more classical skeletal formula, where you don't really draw the extra hydrogens, but you can also do this side as well. Okay, so we have this one, which is our first one, which is nitrogen in the middle, and we have 1, 2, 3, 4 carbons. Okay, but this would be connected to a hydrogen, as is signified on this side. So that would be our first secondary amine, because it's connected to 1, 2 alkyl groups, and then it would be connected to a hydrogen. And we have this one here, which is 1, 2, 3, 4 carbons again, but this is just slightly shifted. The nitrogen is over to the left, or it could be over to the right. It does not matter. Then we have this one, our third and final one. So this is 1, 2, and 3. This is actually a branched secondary amine essentially. So we have 1 carbon here, 1 carbon here, 1 carbon here, and 1 carbon here. So our 4 carbons, we have nitrogen here. We have a branching on this side of things. Okay, So that would be essentially our 3 secondary amines that contain 4 carbon atoms per molecule. Okay. So then, part C. So primary amines can be prepared by the reaction of halogen alkanes or haloalkanes with ammonia or by the reduction of nitriles. Justify the statement that it is better to prepare primary amines from nitriles rather than from halogen alkanes. Okay, so this is a bit more of a complex question, and it's introducing new things, okay, that we might not necessarily have talked about already. Okay, so I'll talk it through. So if we look at halogen alkanes or haloalkanes, we have the further reaction. So we said that it's under reflux, okay? And this means that because it's heated under reflux and things condense and come back down, and gases evaporate and come back down and condense, essentially we have the formation of lots of different products in that reaction liquid, okay? In that flask, we have the production of lots of different products, okay? So essentially, we do get the formation of primary amines, but we also get the further reaction of these primary amines. So further reaction of primary amines. And it forms an impure product. Or we could talk about something called a lower atom economy. Okay, so for all the atoms that are there, the ones that we want, or the yield essentially, is lower. Okay, and that means that there's a lower atom economy. But you can say that, that doesn't necessarily have to be there. You can say that in place of what we've said already. But I thought I'd introduce the concept to you, or some of you might know it already. So if we do it with nitriles, we said that there's no further formation of other products. You only get formation of primary amines, okay? So it's a much more pure primary product reaction or formed, okay? Because there is only one reaction occurring. Okay, so essentially that is why if we were just going for the formation of primary amines, okay, then we'd want to be using the reduction of nitriles rather than using nucleophilic substitution and reaction of halogen alkanes with ammonia, because we get formation of too many different types of amines, okay? So question D is draw the structure of a primary amine with 4 carbons, carbon atoms that cannot be formed from a nitrile. Okay, so it's a slightly more difficult question, but it kind of asks you to think about, how we have the nucleophilic substitution, and how that exactly would work with our cyanide ion. Okay, and here is the formation of that. Okay, and essentially you wouldn't get this. So you wouldn't get this formed with our nitrile. Okay, because our nitrile group has to have a it has to be at the end of a chain. Okay, it has to be the end because we add an extra carbon. We add an extra carbon to the molecule. Okay. So it would either have to be at the end of a chain and add the carbon at the end and then the nitrogen following, or it would have to have, so the way that this nitrogen is attached to this carbon would then have to be attached to something else, another carbon, okay? But in this case, it's not. And that means that this can't be formed by a nitrile, okay? Because we need to add this extra carbon group in when we add the nitrile group, and that means that it just wouldn't form this. In fact, if you wanted to form this as a nitrile, it would be something like H3C, C, C, NH, NH2, CH2, okay? It would have to have this extra carbon group present, CH2, CH3. Okay, so if we wanted to form it with the cyanide ion, it would have to look something more like this. It can't form this at all. Okay, so then part E is a student dissolves a few drops of propylamine in 1 centimeter cubed of water in a test tube. Give an equation for the reaction that occurs and describe what is observed when a universal indicator is added to the solution. Okay, so the equation would be CH3, CH2, CH2, NH2. Okay, it's propylamine, that means 3 carbons, okay? Plus water goes to a reversible reaction of CH3, CH2, CH2, NH3, plus OH minus, okay? This is because we've got hydrogen bonding, and it attracts itself, or it acts as a base, essentially. So, you know, our amine can act as a base. It can take, it's a proton acceptor. It takes a proton from the water, forming a hydroxide ion, and the formation of this, you know, this positive ion here as well, ammonium ion. Okay, so it would turn universal indicator blue. Okay, turns blue. So question F is phenylamine can be prepared by a process involving the reduction of nitrobenzene using tin and an excess of hydrochloric acid. Give an equation for the reduction of nitrobenzene to form phenylamine. Use hydrogen to represent the reducing agent. Explain why an aqueous solution is obtained in this reaction, in this reduction, even though phenylamine is insoluble in water. Okay. So essentially, this is, you know, talking about our reduction of nitriles. Okay, this is essentially what this reaction is. So let's do the equation. So it's C6 H5 NO2 plus 6 hydrogens, because that's our reduction. Goes to C6 H5 NH2 plus 2H2O. Okay. And essentially, this the reason why there is an aqueous solution formed is because we have the formation of a phenyl ammonium chloride salt. Okay. Okay, and that is the exact reason why we have an aqueous solution formed rather than even though the fact that phenylamine is insoluble in water. Oh, bless me. So those are the answers there, but you know, rest assured that we have covered those. Got another question here, which is imipramine has been prescribed as an antidepressant. Okay, so this is another use of the drug. So this is our SSRIs. Okay. As I said, they are, you know, our antidepressants. So the medicine is usually supplied as a salt, okay? And the salt is formed when 1 mole of imipramine reacts with 1 mole of hydrochloric acid. Suggest why the nitrogen atom is labeled B is more likely to be protonated than the nitrogen atom labeled A when the salt is formed, okay? So essentially, this kind of goes back to our electron densities, our benzene rings, and you know how the benzene ring affects the electron densities and, like, you know, withdraws electrons. Okay, so essentially, the lone pair on the nitrogen labeled B is more available. Okay, because there are less, you know, there are less electron drawing groups like these benzene rings. Okay. So the electron on, so the lone pair on the nitrogen A is less available because it overlaps with the delocalized electrons in the benzene groups. Okay, so the nitrogen the lone pair of electrons on nitrogen labeled B is surrounded by these alkyl electron pushing groups. Okay. So it becomes more electronegative on the nitrogen compared to this nitrogen in the benzene, which becomes a lot less electronegative, okay? So if we were to write that down, essentially, we put the lone pair on nitrogen B is more available. The lone pair on nitrogen A is less available, as it's well, we could say as it's delocalized. Localized into benzene rings, okay? Whereas lone pair on nitrogen B is surrounded by alkyl electron pushing groups, okay, which have an inductive effect, okay, because it's pushing the electronegativity onto that nitrogen, okay? Okay, and then part B, again, is a bit of a mean question for me to be asking you, because I know we haven't covered carbon NMR, and yeah, NMR, but I will just briefly go behind the reasoning of this question, okay? So deduce the molecular formula of imapramine and give the number of peaks in the carbon-13 NMR spectrum, okay? So firstly, this is relatively simple. The first part of this is a very simple question, which is just asking the molecular formula of it. So you just go around counting exactly, you know, what species you have, which would be C19, oops, C19, H24, N2, and the number of peaks you'd have in the carbon-13 NMR spectrum would be 11 peaks, okay? And let me tell you exactly why this is. So the carbon-13 NMR spectrum, essentially, it will have different peaks depending on the different conditions that, for every different condition that a carbon group is in, okay? So, for example, if we were to go through here, so we have, if I'm just going to clear, in fact, I'm just going to erase some of the ink I've done on this. So, looking at the different carbons, we have this carbon is the same as this one, okay? So that's 1 overall, okay? You have this one, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, okay? And we have 19, but these, essentially, this carbon here is in the same condition as this one, because it's symmetrical, okay? This carbon here is in the same position, sorry, same environment, or yeah, the same environment as this one here, because, you know, it's symmetrical again. And these carbons here, we don't need to count these carbons here because they're the same as these carbons here, okay? So exactly the same environment, because again, it is symmetrical. So overall, when we count the amount of carbons in different environments, we get 11, okay? So there'll be 11 different peaks on a carbon-13 NMR spectrum. But don't worry if you don't know that, because we haven't really covered that this lesson. That is a bit more of a different question, a bit more difficult to that, okay? So you don't need to worry about that now, okay? So again, those are the answers to those. And then we have here, oops, sorry. We have question 4. So this question is about 3 amines, E, F, and G. So E, F, and G are weak bases. Explain the difference in base strength for these amines and give the order of increasing base strength. So I'm not going to write this one out because I kind of want to get onto the second, the second part of our teaching. But essentially here we have essentially asking about the inducive forces and the availability of the lone pairs on the nitrogen. Okay, so in E we have our nitrogen, which is right next to our benzene ring. Okay, so this means that it's going to be less electronegative, a weaker base, because that electron lone pair is delocalized or overlaps into that delocalized ring on the benzene ring. Okay, in F, our nitrogen, on G and F really, but on F, our nitrogen is as far out as possible from the benzene ring. Okay, so it's less affected by that benzene ring, and therefore it's a stronger base. Okay, in G, what we have here is, although it's attached to the benzene ring directly, we also have these alkyl electron pushing groups. Okay, and it's acting. So although there's an inductive force this way, like negatively taking away from the nitrogen, we also have an inductive force adding to the nitrogen. Okay, so in this case, this one will be sort of like a weak-ish base. Okay, weak-ish. This one will be strong, and this one will be weakest. Okay. So essentially what we need to do is we just need to explain everything that I said and put it into here. Okay, and the order would be E is weaker than G, which is weaker than F. Okay, so B, amine F can be prepared in a three-step synthesis starting from methyl benzene. Suggest the structures of the two intermediate compounds. Okay, for each step, give reagents and conditions only. Equations and mechanisms are not required. Okay, so this requires a three-step synthesis. Okay, but that means that there's only two intermediaries. Okay, because of course the intermediaries are kind of recycled into the subsequent step. Okay, so there's two intermediaries. So the intermediary after so we've got methyl benzene. Okay. We're looking at the formation of amine F. Okay. So then, so essentially what we need to do from methyl benzene, we need to make it a halo alkane. Okay. And then from a halo alkane, so we've got methyl benzene, and we need to make that into a halo alkane. And then from that halo alkane, we'll do a nucleophilic substitution to make it an amine, okay, a primary amine. Okay, so the first step, step one, the intermediary would be C6H5CH HCl, I think. CH. Yeah, I think that should be right. Okay, and the product of, well, in fact, we'll do the conditions. Okay, so for step one, we need Cl2, and we'd also need UV. Okay, because we need to be breaking bonds, adding this chlorine in. So we need the chlorine and the UV. Okay, and step two is our reduction of, step three is our reduction of nitriles, but step two is the nucleophilic substitution of a nitrile group or our cyanide group onto the halo alkane and removing that Cl group, okay, as well. So then, we'd have the formation of C6H5CH2Cn. I think that should be CH2. And essentially, this is when we've substituted in our cyanide group. Okay, and the reagents for this would be we need a KCN. which is where we'd get our cyanide group from. And the conditions would be aqueous ethanol. And then for our step 3, we'd actually, because of course we've got 2 intermediates, but we need to still give for each step, we need to give the reagents and conditions, okay? So for step 3, which is the hydrogenation or the reduction of our nitrile now, so essentially we have a substep here, we get nitrile, and then it goes to primary amine. Okay, so step 3 here, we need hydrogenation, so that's H2 and our nickel catalyst. Okay, so that's quite a difficult question. Okay, so don't worry if you didn't fully understand the answer to that straight away from reading it. But essentially what we have is methyl benzene gets converted into haloalkane, in which case we can add, if we're making a primary amine, we can substitute in our nitrile group, then hydrogenate it or reduce it, and we get the formation of our primary amine. Okay, and that's essentially what we're going through there. Okay, so those are the example questions. So the answers for those questions. And this question I'm actually going to skip because it's actually very mean of you. Because again, it's got another one of these spectra. So I don't think that's really an appropriate one for me to ask. And essentially, we can answer this one standalone. So this one here is give a reagent that could be used in a test tube reaction to distinguish between benzene and cyclohexene. Okay, describe what you would see when the reagent is added to each compound and the test tube is shaken. Okay, so you've got benzene, okay, benzene and cyclohexene. Okay, so essentially we have an aromatic group, and then we have a straight alkene, okay, and a cyclic alkene, okay, so aromatic and cyclic alkene, okay. And one way of differentiating between these is by using bromine, okay. So bromine, which is orange, so it's a bit like the reaction with bromine water, but in this case we're using just bromine gas, okay. So bromine, or you could use bromine water to be fair. Okay, so bromine, and that's orange. With benzene, because it's not an alkene, or a cyclic alkene at that, there'll be no change, okay. And then with cyclohexene, cyclohexene, there will be decolorization. Oops. Because just like the the bromine water reaction, you get the reaction between the cyclohexene and the bromine, and we get addition. Okay, so essentially that is the answer for that. So we've covered our first learning, our first section of our learning objectives, really. So that's our amines ticked off the list. So we know all of these things. We know the functional groups of amines and how to name them. We know the properties of primary amines, including boiling points and solubility. We know how to make amines, both linear and cyclic. We understand the reactivity of amines and how their structure causes this. We know that amines have behave as Bronsted-Lowry bases. We know how amines' basic strength differs from each other and ammonia. And we've described and drawn the nucleophilic reactions of amines. Okay, so I'll probably answer a few questions here. We don't really have time for too many. I think you can still ask our moderators them through Microsoft Teams, but I'll probably pick 1 or 2 questions for us to answer, and then we'll move on to our second section. So I've left the like an active poll open for you if you want to submit a few questions. So I'll give you a minute to do so. But of course, you need to press on to make sure that we cover all our topics today and that we have a nice hour lunch break, okay? So I'll give you a minute to do that. If none of you have questions, that's perfectly fine. But of course, if you do have questions, you can always ask the moderators. I'm sure they'll be able to help you. So I'll give it another minute because obviously, it does take a little bit of time to write out questions. And of course, we're not doing a Microsoft Teams quiz at this stage because we've done our Slidos, okay? We've done our Slidos, we've kind of integrated them through, and we've made sure to re-jog our knowledge as we make our way through our teaching material, okay? So I'll wait another few 30 seconds, 45 seconds. Okay, so one question here is for reaction conditions. Isn't saying in a closed system the same as under pressure? And that is not the case, okay? And I understand as heat goes up, then you have pressure, but essentially it's not the same. So a closed system is trying to get at the fact that we've got, evaporation of liquid or stuff from the reaction. It gets condensed and it comes back down, okay? So that's essentially what we're looking at for a closed system. There is actually, there would probably be a very small difference in pressure, but it's not something that's notable, and that's not really what we are kind of targeting in that. The increased pressure would be something for like, our nitriles or reduction of nitriles. We need a little bit of pressure for the nickel catalyst, okay? And could you please go over again about the basicity of amines increasing? Okay, I'll do that in a second. Why do larger amines have a lower boiling point? I think we went through the general formula for that. Wouldn't you still have? Okay, I think that's probably a question for the moderators. Because in terms of our slides, I think we covered just the general things, but for the more detailed question, I think the moderators might be better at answering that question. Okay. So is a tertiary amine a weaker or stronger base than a primary amine? It's a weaker base because primary amines are more soluble than tertiary amines. Even though tertiary amines have additional inductive forces, they're not as soluble, and that means that they're not as strong bases. Okay. And then you have, wouldn't you still have hydrogen bonding with tertiary amines between themselves as the hydrogens on the alkyl groups would bond? No. So essentially we need to have sort of a difference in electronegativity between the nitrogen and the hydrogen for there to be hydrogen bonding between tertiary amines. There's not the same electronegativity or delta positivity on hydrogens in alkyl groups as there is when you have the difference in electronegativity on a nitrogen to a hydrogen group. Okay, so what I'm going to do now is I'm going to quickly go back over to slide 36, I believe, and that is where we had our basic strength, and I'll just quickly go over this again. Essentially, we have our inductive effect. So this is our basicity, our base strength. We have ammonia in the middle. Okay. And then we've got this inductive effect. Okay, so let's talk about the phenol amine first, or phenol amide. So basically, the electrons overlap and are delocalized into this benzene ring. Okay, and this pulls the electronegativity from the nitrogen. Okay, and this makes this delta negative smaller. Okay, so it's not as polar, and that means it's reduced basicity. Okay, if we have a look at the inductive effect, the electrons, so we have these alkyl groups, okay, and these alkyl groups are electron pushing. It pushes the electrons towards the nitrogen, and this makes this delta negative bigger. Okay, so it becomes more polar, and that makes it a stronger base. Okay, so essentially that is the answer for that question that you had there. So going back to this, we'll move on to this. So I want you guys to rate your knowledge of this section now that we've covered it. And, obviously we can still cover things. Once we've covered all of our teaching topics today, we can go back. But I want you guys to rate your knowledge in this section now. I think you guys have done really well considering we had our quizzes, and you guys seem to perform really, really well in those. So I think your knowledge is quite good. but if you could rate your knowledge on this section now that we've covered it, let me know, and then we could possibly go back on things later on at the end, towards the end of our session. Okay, so we've got someone in the middle. So on 5. Okay, that's good. Okay, good. And of course, this is, sort of going over multiple exam boards. So there might be some smaller details that, some of you might feel like you might not have covered, but unfortunately, we're not able to cover every single small detail because we are trying to cater for everybody. But it's looking like most of you are finding this, your knowledge in this section is good. And I'm sure with a few more past paper questions that you probably boost that knowledge and boost your confidence on that, okay? So I think our average or our most common is 4, which is good because we're skewed more over to the higher end of things, okay? So then, now what we're going to do is we're going to cover our second topic, okay, which is amino acids, okay? So amino acids, the learning objectives here are quite small. This is a smaller section. So we want to know the structure of generic amino acids. We want to explain why amino acids have both acidic and basic properties, including the formation of Zwitter ions. We want to be able to draw Zwitter ions and amino acids in both acid and alkaline solutions, okay? So those are the 3 learning objectives we want to really cover for this section, okay? So then we've got our exam boards. So we've got AQA, again, small section. You can take a picture of this if you want, or you can take a screenshot, whichever suits you. We have our OCR exam board. Again, take a picture or a screenshot using print screen, or of course you can flick back to it on the slides. And then we have our Edexcel exam board. Okay. So this is a very small section. Hopefully we'll be able to cover it by or just after our lunch break, and we'll move on to our last section, which is a little bit more complex, let's say. So then. Amino acids. So there are 20 naturally occurring amino acids, okay, in nature, okay, and they all differ by R groups, okay, but they all have the same basic structure, okay. So essentially, they have 2 functional groups. So they've got the carboxylic acid, and they have the primary amine group, okay. This is why they're called amino acids, because they've got carboxylic acid, and they've got the primary amine group, okay? Amino acids are the monomers of proteins. So essentially, proteins are made up by, hundreds and thousands of these amino acids, or, quite a few of these amino acids. So they join together, they react with each other, and they form these proteins, okay? So naturally occurring amino acids are known as alpha amino acids, okay? And this is where the carboxylic acid group and the NH2 group are attached to the same carbon, the same carbon, okay? And this means they're chiral, they have enantiomers, okay? And so essentially the lack of the plane of symmetry means that there will be there will be 2 stereoisomers of an amino acid, apart from the most basic amino acid, which is glycine, which this R group is actually hydrogen, okay? So in that case, there won't be any enantiomers. But in all the other more complex amino acids, there will be 2 stereoisomers isomers of the amino acids, and one of them, well, essentially there will be non-superimposable mirror images of each other, okay? And that means that they're isomers, which means they can't be, however many times you flip them in 3D space, they can't be overlapped on each other because they're non-superimposable, okay? And it's all spirals around this chiral carbon atom in the center, okay? So carboxylic acid groups are acidic, okay? So if they lose a proton, okay, a proton donor they are a Bronsted-Lowry acid, okay? So Bronsted-Lowry base was where they gain a proton, okay? A Bronsted-Lowry acid is where you lose a proton, okay? So here we can see the deprotonation, or the removal of this hydrogen group to form this carboxylic acid, this acidic form of this carboxylic acid, okay? And amine groups are basic, okay? And we've already talked about this when we were looking at our primary amines, secondary amines, phenol amine, ammonium, in terms of their base, okay? They gain a proton, and that means that they are Bronsted-Lowry bases, okay? And here we've got the protonation of an amine, okay? So we've got NH3 plus, okay? And our R group here. So amino acids have both of these. So what does that make them? That makes them a Zwitter ion, okay? So they have both of these groups. So they can have this, they can be deprotonated and they can be protonated because they have this amine group and they have this primary amine group, sorry, and they have this carboxylic acid group. So a Zwitter ion is an ion that has a permanent positive and negative charge, and the overall, and the compound is neutral overall, okay? So it has a positive and negative charge, like we've just seen. This positive section over here, negative section over here. It's the carboxylic acid. This is our primary amine. And essentially, because we have this permanent positive and negative charge, the overall compound is negative, okay? So that is what a Zwitter ion is. So having a look at these Zwitter ions in a bit more detail, let's have a look at them when they're in different conditions, okay? So in an acid condition, we have, or in a strongly alkaline condition, in fact, yeah, let's talk about strongly alkaline conditions first. So erase all the ink. So in strongly alkaline conditions, essentially the amine group accepts an electron, okay? And that means that the carboxylic acid group does not lose its proton, okay? And the overall charge of this is positive, okay? And we can see this here. So in strongly alkaline conditions, okay, it accepts a proton, and then it forms this more it has a proton, and it comes in overall charge of positive, okay? Because you've got this positiveness here. Okay, let's just ignore that. Okay, so this is in alkaline conditions. Oh, actually, sorry. I think I might have got the slides mixed up. Okay, so anyway, in strongly alkaline conditions, the amine group does not accept a proton. Okay, so I think, sorry, this was in acidic conditions. Let me get rid of that. So this is in acidic conditions. Okay, and this is in alkaline conditions. Sorry, I just mixed that up. So in strongly alkaline conditions, the amine group does not accept a proton, okay? The carboxylic acid group loses its proton, okay? And overall charge is negative, okay? So essentially, we have this deprotonation, okay? This deprotonation of the carboxylic acid group, okay? And in acidic conditions, we have the protonation of our primary amine group, okay? And in a neutral solution or neutral conditions, we'd have a neutral Zwitter ion, okay? So you've got protonated, Zwitter ion, deprotonated, okay? So in summary, and I'll just go over these again, amino acids have two functional groups, which is CaOH and NH2. They are naturally occurring, and we require them for building proteins. The R group varies, okay, so that's what differs between amino acids, okay. Amino acids have both basic and acidic properties. They form Zwitter ions in neutral solutions. They become protonated and positive in acidic solutions, and they become deprotonated and negative in acidic solutions. So let me go over all those again quickly, and then we'll move over onto some Slidos, okay? So, as I said, they are naturally occurring amino acids. They differ by R groups. So this R group here, in the most basic form, which is glycine, it would be H, but in other amino acids, it differs. They have these two functional groups, which are carboxylic acid and primary amine groups. Naturally occurring amino acids are known as alpha amino acids, and they are chiral, okay? So they have stereoisomers of themselves, apart from glycine, of course. They have stereoisomers of themselves, okay? So carboxylic acid groups are acidic, and they can lose a proton, okay? And amine groups are basic, and they can gain a proton, okay? So Zwitter ions, where they have an ion that has a permanent positive and negative charge, and the overall compound is a neutral charge overall, okay? So then, in acidic conditions, okay, so this should be acidic, they become pronated, okay, because remember, if it's in acidic conditions, just think about it as if it's trying to oppose that condition, okay? So it's becoming more basic by accepting that proton, okay? So that amine group accepts a proton, the carbon group does not lose its proton, and the overall charge is positive, okay? And it becomes pronated. In acidic conditions, it becomes pronated and it becomes positive, okay? In alkaline solutions, let me clear all this up as well. In alkaline solutions, it becomes depronated, okay, because it does not accept a proton, and the carboxylic acid loses its proton because it's trying to oppose a chain. So in alkaline conditions, the carboxylic acid becomes more of an acid by giving away its proton, okay, and that means that the overall charge is negative. So alkaline conditions, strongly alkaline conditions, it's depronated and it's negative, okay. Gone through all of those. So then, what is the most basic amino acid and what functional group does it have? Okay, so I've talked about this a few times. You might not have heard it, and don't worry, but I've talked about it 2 or 3 times in passing while I've been doing these slides. Okay, so what is the most basic amino acid and what functional group does it have? Okay, so I'll let a few of you answer that question first. One answer so far. I think we need a few more than one answer. Okay, we've got 2, 3. Okay, keep it coming, guys. So again, I hope you guys are really enjoying the Slido. I'd probably keep it up, obviously, for the next half of the session as well, or the last part of the session as well, because we will be using Slido throughout. So yeah, it's important to keep it up. But obviously, if for whatever reason you close it down or it closes itself down, we have a QR code at the top, so you can always see that. And the Slido is #K981. Okay, so a few more of you guys to answer that question. Give you another 20 or so seconds. Don't worry if you don't know it, because I did only say it in passing. I was seeing, if you did hear me say it, then that's really great. But if you didn't, no worries. Okay. Okay, so let's have a look at the answer. The correct answer is glycine, and its functional group is H. Okay, so really well done to you guys that did that. For those of you that put alanine in H, well done for remembering that the functional group that it has is H. But alanine, it does sound a lot like glycine because it's got that "ine" in the end, but the correct answer is glycine and H. Okay. So the next question is, how many naturally occurring amino acids are there? So you've got 30, 25, 20, 15, or 10. Okay, which one is it out of all of those? Got quite a few people answering. This one I mentioned a bit more than the last question. Okay, good. We'll just give you another 15, 20 seconds for the rest of you to add your answers in. A few more seconds. Okay, so let's have a look at the answers to this. Okay, so the correct answer is 20. Wow, almost all of you got that one. That's really good. So the correct answer is 20. Okay. Then what property of amino acids allow them to have optical isomerism? Okay, there's an active poll again. This one's saying chirality, chiral carbon, needs to be chiral. This is good. This is good. We're all on the right track here. Okay, yeah. So essentially, for amino acids to have optical isomerism, they need to be chiral. Okay, so they need to have that chiral carbon in the middle that allows them to have that optical isomerism, those stereoisomers that, as someone just said, have 4 different atoms or groups attached. And if you did a mirror image of them, it would have, they would be non-superimposable. Okay, that's really, really good. So moving on to the next one, what is a Zwitter ion? Okay, so I'd like to hear your thoughts on that one. So what is a Zwitter ion? Okay, good. Okay, have a few more of you guys answering. So yeah, I mean, you guys are hitting the nail on the head. Yeah, an ion with a permanent positive and negative charge, and overall neutral. Okay, separate positive and negative charge, no idea. No worries. So essentially, what everyone's saying is it's an ion with a permanent positive and negative charge, and overall compound. The overall compound is neutral. Okay. So that's essentially the definition of a Zwitter ion. Okay, and they can become protonated and deprotonated. So in neutral, they're both protonated and deprotonated. In acidic, they are protonated, and in alkali conditions, they are deprotonated. Okay, so it looks like the vast majority of you guys have really got that one. Don't worry if you haven't. It has been a quick little section that has. So don't worry about that too much. Okay, so then let's have a look at the next question. So in strongly acidic conditions, what happens to a Zwitter ion? Okay. There's 4 potential answers. Protonated accepts an electron. Sorry, accepts a proton. Protonated doesn't accept a proton. Pardon me. Deprotonated accepts a proton. Deprotonated doesn't accept a proton. Okay, so you really need to think about what protonated means, and then you need to think about what happens in acidic conditions. Okay, so what happens to a Zwitter ion in acidic conditions, or strongly acidic conditions, should I say? And again, don't worry if you don't know. These are quiz questions, and we do have the we do go over the correct answer. So it doesn't matter if you don't know it. Just make a note of the answer. Maybe you can come back on that to revise on. Yeah. So let a few more of you guys answer this. Okay. So the correct answer that 84% of you guys got right is pronated accepts an electron, and that is correct. So really well done to you guys. And I think that about ties us up at 12:30. So it's time for our hour lunch break. So we'll be back at 1:30. We'll go over some exam questions. There's only a few past paper questions for that section, and then we'll finish off with our final teaching block. Going over our last bits of our teaching material. Okay, and that's basically on proteins. Okay, so then I'll see you at 1:30 after you've had your lunch, have a stretch, have a drink, and I'll see you at 1:30. Okay, great. Thank you so much, guys. Okay, so hopefully you guys can hear me again, and hopefully you had a really nice lunch break as well. I know I did. I had a really nice lunch. So hopefully you guys are refueled and ready to go. So we just finished up on the Slido last time, and I think we have a few exam questions for us to do before we move on to our next topic. Okay, so these ones, they're not particularly long, because it was only a small topic that we covered before we finished for our lunch break. So if we have a look, we've got two questions here. Okay, they're both multiple choice questions. So the first one is, which structure shows 2-amino butanoic acid as a Zwitter ion? Okay, so in this case, we're looking for a Zwitter ion. Okay, and so if we just have a look now, we can immediately negate this one here and this one here, okay? Because those are not Zwitter ions, okay? And the second thing we need to have a look at is the butanoic acid, okay? 2-amino butanoic acid, okay? And essentially, because you've got this 2 here, it's from the point where our butanoic acid is. So our butanoic acid, or the oic acid, is the first carbon, and then our amine, or our amine group, should be on our second carbon. Okay, so having a look at this one here, if that's our first carbon, that's our second, and that's our third. So this here would be 3-amino butanoic acid. Okay, but if we have a look at this one here, this is our first carbon, this is our second carbon, and here we have our amine group. Okay, so we can confidently say that question B is the right answer for this question. Okay, now then, let's move on to C. So which structure is formed by aspartic acid in solution at pH 12? Okay, so at this point here, we're looking at a strong alkaline solution. Okay, and if you remember, a strong alkaline solution, we are protonated, which means the carboxylic acid is changed to COO negative, but the NH2 is still NH2, okay? Because remember, it's our primary, so we've got our primary amine, and it stays as a primary amine if it's in strong alkaline conditions. So let's have a look at this, okay? So after looking at this, we need to make sure that we have H2N. Oh, sorry, yeah, H2N. So we can get rid of this one here. We can get rid of this one here. And we also need to make sure that our carboxylic acid groups have been converted into COO negative groups, okay? And in this case, we've only got one of them being converted, so we're looking at this one here. So both of them need to be converted, okay? So the answer for us is D, okay? That's a super simple question for us, okay? And having a look at question 7 as well. So use a data booklet to help you answer this question. This question is about amino acids and peptide amide links. Draw the structure of a Zwitter ion formed by phenol alanine. Okay. So this one is a little bit of a difficult question if you don't have data booklet for this question. But what we'll do is we'll flash it in. And we'll talk about them. So just to remember, a Zwitter ion is a molecule or ion having separately positively and negatively charged groups. Okay, so we need to make sure this has positive and negatively charged groups, okay? And again, at high pHs, so looking at this question here, so this is our answer for part A, and you know, we've got our aromatic ring there, and essentially this is what we're looking for, okay? And then for part B, we're asked to draw the structure of serine at high pH, and I think this is where we need our data booklet to make sure that we've got the right residue, or R, for serine, because it is an amino acid. And essentially at high pH, we're looking at deprotonated. So that means our COOH needs to go to a COO negative group, and that is why we have our carboxylic acid converting into this here, okay? So essentially, that is how we do those questions. So that's our amino acids ticked off, okay? So we've covered all these learning objectives, okay? So we know the structure of the generic structure of amino acids. We can explain why amino acids have both acidic and basic properties, including the formation of Zwitter ions. And we're able to draw out Zwitter ions and amino acids in both acidic and alkaline solutions, okay? Done all of those things, which is really good. So now I'm going to give you guys just a chance to ask any questions. I won't leave as much time to answer these questions because, of course, you know, that was a smaller teaching area, and we have got, you know, about half the presentation left. But if you guys want to ask any questions, I will try my best to answer them, or the moderators hopefully will be able to answer them if you put them onto the Microsoft Teams. Okay, but we won't be publishing the Microsoft Teams questions. This is only the Slido questions we'll be looking at here. Okay. So if you want to have a look, if you want to go to our Slido, and if you've got any Q&As, I'll give you about a minute or two to ask any questions. And of course, I can flick back through the slides to, you know, just to help answer those questions, okay? And then what we'll do is after that, we'll rate our knowledge in this section. It is a small section, so hopefully you guys have understood quite a lot of it. And then we'll move on to our last section for the day, okay? So again, I'll just give you a few minutes to write any questions, and I'll try and answer them as best I can. So if you're not on the Slido, make sure to scan the QR code or use the code #K981. And that should allow you to access the Slido and ask any questions. Could you go to the 2/3 step equations when there's enough time? That's perfectly fine. We can actually brush through them again in a second. If you're talking about a two-step, in fact, the 2-step, 3-step equations, I assume that's the first half. Yeah, well, we can go back over those at the end. In fact, I'll just make a note of that. So we can go through those at the end. If there's enough time, we can go through those at the end. Okay. Okay. I think that is the only question that we've got. So of course there's going to be another Q&A at the end. So if you think of a question in the meantime, you can always ask it at the end and we can go over things. But for now, what we're going to do is, how do amines act as Bronsted-Lowry bases? Well, that's when they're in an acidic condition, okay, they act as Bronsted-Lowry bases because Bronsted-Lowry bases accept protons in acidic conditions. Amines, because they have that primary amine group, they can take on or get protonated and take on a proton, and that means they're acting as a Bronsted-Lowry base. Okay, and similarly, if they're in alkalinic conditions or alkaline conditions, then they will act as a Bronsted-Lowry acid because they will deprotonate. Okay, and that carboxylic acid will turn to a COO negative group. Okay, and that is how they act as Bronsted-Lowry bases. In fact, that was amino acids, but amines, nonetheless, it follows the same thing for Bronsted-Lowry bases. Okay, so if you guys could rate your knowledge on this section, and then it means that if you guys want to go over anything again, we can always go back at the end. But hopefully you guys, seeing as you guys didn't have too many questions, hopefully you will feel relatively comfortable on it. Okay. So I'll give you a second to do that. Good. Okay. Okay, so what we can do is, so our mean score is 3.7. What we can do is you can always go back over this at the end, just so once we've covered our knowledge, then we can come back over it and make sure that we know everything. Okay. Okay, so moving on to our final section, which is proteins. Okay. So the learning objectives is to describe polypeptides as a sequence of amino acids joined by peptide links and draw peptides from amino acids. Okay. The second learning objective is to explain the formation of the primary, secondary, tertiary structure of proteins. We also need to know that the peptide links can be broken by hydrolysis, producing the constituent amino acids. We need to understand the importance of hydrogen bonding and sulfur bonds in proteins. Pardon me. And we need to know the properties and functions of proteins. Okay. We also want to describe how amino acids can be separated and identified by thin layer chromatography. Okay. So there's a few learning objectives that we need to know for this section. And this section can get a little bit confusing, so I'll make sure to summarize every now and then. So for the exam boards and specifications, we have AQA here. So if you want to take a picture or a screenshot, or you can just flip back through the slides. Again, we have OCR here, so you can do the same. And this just allows you to make sure that you know what applies to you, and what sections of what we're talking about are crucial for your exams. Okay. And finally, we've got Edexcel. Okay. Starting with our last section, proteins. So proteins are made of polypeptides. Okay. And polypeptides are essentially long chains of amino acids. Okay. And that's what we were talking about before when we started off with the topic of amino acids. So we were saying that amino acids are the monomers of polypeptides. Okay. So the individual subunits that make up polypeptides. Okay. So proteins are made up of these polypeptides. And proteins have 4 levels of structure. Okay. So the primary level of structure, so this is the first level. So the primary level is the order of the amino acids in the polypeptide chain. Okay. So as we said, we have 20 amino acids. Okay. And because you have 20 of these, this primary order is essentially just if you have, for example, glycine and then arginine and then glycine again, and then alanine. So this is what we say is the primary structure, okay? Because this is the order of amino acids in a polypeptide chain, okay? Secondary level, or the second level of structure, is the hydrogen bonds between different amino acids, okay? So amino acids can hydrogen bond between each other because they have oxygens and they have, they have polar oxygens and they have polar hydrogens as well, okay? So this is the hydrogen bonds between the different amino acids, and this means that it folds in specific ways in 3D shape, okay? So the tertiary structure of proteins is the interactions between the R groups. So we talked about amino acids, having this general structure. In fact, yeah, let's do this. See, OOH, R group, okay? So this is the interaction between these R groups here and other R groups of different amino acids, okay, in this chain, okay? And the quaternary structure is the coming together of more than one polypeptide, okay? So when you've got, let's say you've got two chains of polypeptides, okay? These can come together to form a more complex protein. For example, hemoglobin. So hemoglobin is an example of a quaternary structure protein because there's multiple different proteins that come together to, polypeptides that come together to form a very complex protein, okay? So let's have a look and break down these individual structures a bit more so we can understand them better, okay? So the primary structure, okay, of a protein is the amino acids, okay, and their order, okay? So amino acids can undergo condensation polymerization, okay? And this is essentially polymerization which produces water, hence why we get condensation from, okay? Produces water. And we'll see this in a second when we have a look at the reaction, okay? So there are amide linkages or peptide bonds, okay? And the formula for a peptide bond is this, okay? So it is C double bond O, N, H, 2. In fact, yeah, NH, there we are. And essentially that's what a peptide bond is, and we'll have a look at this in a second, okay? And that's between the carboxylic acid group of one amino acid, okay, and the amide group of another, okay? And this produces a water molecule, hence why we call this condensation polymerization, okay? So here we have our primary structure, okay? So here we've got our individual amino acids. So this is amino acid 1, amino acid 2, and amino acid 3, okay? And we can see here, this is where they bond, okay? This is where there's going to be a bond between this carbon and this nitrogen, okay? And we're going to get a formation of the peptide bond. In fact, I think this slide was slightly wrong. It shouldn't be that. It should just be this structure here, okay? So it's just CON, okay? And H, sorry. So if we have a look at the actual reaction, this is a condensation polymerization. So here we have the formation of a tripeptide, i.e. it has 3 amino acids, okay? And a polypeptide is just a peptide that contains multiple amino acids, okay? So dipeptide would be 2, tripeptide 3, and then polypeptide, multiple. It could be, 1,000, or it could be, 5, okay? So these peptide linkages we can see here. So this is that C double bond O, O-N, sorry, I think that should be E. Yeah, in fact, I think that is slightly wrong. And H. Okay, so this is the formation of a peptide link, okay? So we get the formation of these the waters from here, and that is how we get our peptide links, okay? So the primary structure, we've got these compounds formed by the linking of amino acids are called peptides, okay? So as I said before, 2 peptides is a dipeptide, 3 peptides, tripeptide, 4 peptides, sorry, 4 amino acids, tetrapeptide, and many amino acids, basically 5 or more. It's just polypeptide, okay? So this is our way of classifying peptides, okay? So polypeptides can be broken back down into amino acids by hydrolysis, okay? And this needs to have the addition of water, okay, because of course we used our water up in that reaction, okay, and then an acidic catalyst, which is HCl, okay, and this way we can re-break these polypeptides or peptides back down into their constituent amino acids, which are all individual, okay. So our method here would be to boil the polypeptide, okay, so we heat it up and boil it in water with 6 moles per decimeter cubed or concentrated HCl, okay, and this acts as, so this is an acidic catalyst, okay, this acts as a catalyst to hydrolyze these polypeptides back down into their the constituent amino acids, okay, and you'll need to do this for 24 hours to completely break down a solution full of polypeptides, okay. So the body hydrolyzes protein in food, and it uses other enzymes, using other proteins as well, using enzymes, okay. But if you think about it, this is how we actually break down our foods and absorb the nutrients from them. So when we have protein, we hydrolyze them, break them down into their constituent amino acids, and then absorb those amino acids, and that goes into muscle regeneration, tissue building, that sort of thing within our body, okay. And we use enzymes, okay, which are other proteins essentially, which are catalyzing the breakdown of these polypeptides, okay. So the order or the primary structure of a protein, or the order of the amino acid sequence, is very, very, very important, okay, and it affects the secondary and tertiary structure. So one wrong amino acid can cause a protein to become non-functional, and some of you guys that do biology might understand this to be an example to be sickle cell anemia, okay. So sickle cell anemia or sickle cell disease, people who have it do not make hemoglobin properly, and hemoglobin is a substance in red blood cells which allows oxygen to be carried around the body, okay. And normal red blood cells are flexible and disc shaped, okay, so they kind of look like this, okay. But in sickle cell, they look more like that, okay. So they lose their shape and their rigidity, okay. So they lose their shape and they become more rigid and more like a crescent, okay. So this is nice and flexible, and the sickle cell, okay, sickle cell is now rigid, okay, and it's lost its shape. It's more like a crescent, okay. So what happens is, because the hemoglobin inside them clumps together, inside the red blood cells clump together, this is why we get this formation of this rigid, sorry, bless me, rigid crescent-like structure, okay. And essentially, these cells give rise to the symptoms of sickle cell disease because they don't live as long as normal red blood cells, and they can become stuck in blood vessels, and they also don't carry as much oxygen around. So people with sickle cell are often very, very tired, and they're also at risk of certain other infections or diseases. But actually, interestingly, those with sickle cell are actually much more or sort of immune to malaria. Okay, so you have actually a selective pressure for more sickle cell, for individuals to be sickle cell positive in Africa due to the endemic malaria that is there. So those with sickle cell survive, well, have a greater chance of survival in if they were to be infected by malaria, and therefore there's a selective pressure in Africa. So it's a very interesting topic. You'll probably learn more about it in biology if you do biology, and probably learn more about the details and the exact selective pressures and why it's come about. But essentially, this is all caused by one wrong amino acid. Okay, so it's a switching of one amino acid, and this is what causes it. So, sorry, and this is what it causes. So the primary structure of a protein is extremely, extremely important for the function of the protein. Okay, and that's why it affects the secondary, tertiary, and then the quaternary structure as well. So let's have a look at the secondary structure of a protein. Okay, so polypeptides fold around themselves due to hydrogen bonding, okay? And the hydrogen bonds are between the oxygens, double bonded oxygens, and the hydrogens in the NH, okay? And we can see this here. So we've got our double bonded hydrogens, sorry, our double bonded oxygens and our hydrogens, okay? And there are two different shapes that polypeptides can form. We've either got our alpha helix or alpha helices, or our beta pleated sheets, okay? So our alpha helices is kind of like, like a coil, essentially, okay? And you've got, bonding between individual bits, which holds this shape, and that's why it forms this helix structure, okay? And then you have a beta pleated sheet, okay? And here it's more of like a flat. So you can see at this point here, it's like a flat thing. And, as the protein folds around as well, you get the interactions between different beta pleated sheets, okay? And it's probably worthwhile knowing at this point, because I remember when I learned secondary structure of proteins, that I thought a protein could only be one or the other. But in reality, we actually have a mixture of alpha helices and beta pleated sheets in complex proteins, okay? So, a lot of the proteins in your body have sections which are alpha helices and some that are beta pleated sheets, and it all works together and interacts with each other to produce a functional protein, okay? But for now, the secondary structure is the way that polypeptides fold around themselves due to hydrogen bonding, and the hydrogen bonds are between the double bonded oxygen from what's left of the carboxylic acid and the hydrogen in the from the primary amine group, essentially, okay? So moving on to the tertiary structure, okay? So tertiary structure is the interactions between R groups of the amino acids, okay? So they include hydrogen bonding, which we can see here. So if we have our R groups, okay, so this is an example of an R group, and this again is an example of, this again is an example of an R group. We've got an interaction here, so we can get hydrogen bonding between these R groups, okay? We can also get hydrophobic, hydrophilic interactions, okay? So if a portion is hydrophobic and a portion is hydrophilic, they will react in a certain way. If both are hydrophobic or both are hydrophilic, they will also react in a certain way, okay? And this is all interactions between the different R groups present on the amino acids, okay? The third way that you can get tertiary structure interactions between R groups is dipole-dipole interactions and ionic bonding, okay? And here you've got another example. So you've got this really nice long R group here, and this other one here as well, okay? And there's a permanent dipole-dipole between this NH3 plus and this OH minus, okay? And that forms an ionic bonding, okay? So this holds the structure together, okay? And then the fourth and final way you can have structure or interactions is these disulfide bridges, okay? So here we've got this disulfide bridge, and it bridges so it connects one side of a polypeptide chain to another through this disulfide bridge here, okay? So you've got these four different methods, okay, of interactions between R groups. So you've got hydrogen bonding, hydrophilic and hydrophobic interactions, dipole-dipole interactions, and ionic bonding, and disulfide bridges, okay? These are the four different ways there can be interactions between R groups of the amino acids, and that's what we call the tertiary structure. So here's an example of, tertiary structure, and you can have all these things. You will have all these things interacting with each other on in every single protein, just at different places, okay? So here we've got an example. So we've got our polypeptide chain, which is a very, very long structure, okay, full of lots and lots of different amino acids. We've got ionic bonding, we have hydrophobic interactions, disulfide bridges, and hydrogen bonding, okay, or H bonding. So all of these interactions can happen simultaneously. It's just at different parts of the polypeptide chain, okay? And this is what we call tertiary structure. So our tertiary structure is the interactions between the R groups of amino acids in these different ways, okay? So switching to some Slido questions, we have our first one here. So how many levels of structure does proteins have, okay? So if we have a few answers to this. So we've got 2 people that have submitted their answers. Let's have a few more people. 3, 4. Okay, that's good. Let's have a few more. Got 15 now. We'll wait until we have about 25, 30, 35. And I realized I made a mistake on one of the slides, so we'll go back to it just to make sure that you guys are clear on what a peptide bond looks like before we do any past paper questions involving that. I think that'll probably be useful. Okay, so we'll wait for a few more people. Okay, so how many levels of structure do proteins have? We have 4 levels of structure. That's primary, secondary, tertiary, quaternary. Okay, so primary is the order of amino acids. Secondary is the interactions between the H bonding and the folding, the subsequent folding of the primary structure or the amino acids. Tertiary is the interactions between the R groups between amino acids, between the R groups of amino acids in a polypeptide. And then quaternary structure is the interaction of multiple polypeptides together, okay, when they come together to form a more complex protein, okay? So here's a second question. What is the primary structure of a protein? So I want you guys to explain to me what the primary structure of a protein is. Okay, good. Sequence of amino acids. Sequence order of amino acids, good. Amino acid sequence, good. So a few more people chime in. Good. Okay. So yeah, we have a good amount of people saying the correct answer. So it is to do with the sequence or order of amino acids in a polypeptide. So that's the primary structure. Okay. So let's move on to the second question, which is, what is a secondary structure of a protein? What is a secondary structure of a protein? Okay, so we've got beta-pleated alpha helix, okay. The initial folding of the amino acid chain. The linking of amino acids. Okay. Hydrogen bonding between different amino acids. Okay. So we have a range of answers here, okay, and all of them are in the right area, okay, but if we go back, and we'll summarize after we've done these Slido questions, okay, so but if we go back, it's the amino acid sequence, the primary structure, and the hydrogen bonding between the amino acids, which forms a folding of the polypeptide in 3D space to form either an alpha helice or a beta pleated sheet, okay. This is due to the hydrogen bonding between the amino acids. Okay, so a lot of you guys are getting the right sort of the area, targeting the right area. So we've got beta pleated sheets or alpha helix. those are two types of structure. Those are the two types of structure you can get. The definition is the 3D folding of an amino acid chain in 3D space through H bonding between them. Okay. So then, what are the two types of secondary protein structure? I think you guys will do really well on this one because you said it so many times in the last question. Okay, so what are the two types of secondary protein structure? Yeah. Okay, we have a lot of people saying the right things, and that's really good. It's really, really good. So alpha helix and beta pleated sheet. Okay, so that is the correct answer. Okay, yep, through hydrogen bonding. Great. Yeah, an even more detailed answer. Okay, great. So those are two types of secondary protein structure. Okay. So moving on to the next question, what is the tertiary structure of a protein? Okay. And the reason why I'm getting you to write all these down is that it helps, rather than give you a multiple choice question, it helps you really memorize and stick in your brain what the actual definition is, and hopefully you'll be able to remember it a bit better. Okay, so you've got interactions between R groups, how the proteins fit together, and, alpha helix and beta pleated, 3 coiling of the chain. Polypeptide chain with further bonding, disulfide bonds, ionic bonds, hydrogen bonds, hydrophobic interactions. Wow, some of you guys are really, really nailing these answers. Okay, so essentially it's the interactions between R groups and the further folding. So the interactions between R groups with different amino acids and the further folding of a polypeptide chain due to hydrogen bonds, hydrophobic interactions, ionic bonding such dipole-dipole, and disulfide bridges. Okay, so you guys have really, really nailed that one. It's different to just our normal alpha helices and beta pleated sheets. That's formed due to our H bonding between amino acids. Okay, whereas a tertiary structure is to do with the R groups, the interactions between different R groups of amino acids. Okay, and their interactions together to form either ionic, hydrophobic, hydrophilic, disulfide bridges, and oops, accidentally switched. But yeah, okay, we'll move on to the next question. So what types of bonds can we, in fact, no. let's move on to this one. So what is the quaternary structure of a protein? Don't want to get too far ahead of ourselves there. That's the next question. So what is a quaternary structure of a protein? So what is the quaternary structure of a protein? So we're not talking about bonds here. We're talking about the quaternary structure of the protein. Wow, so one person put a very detailed answer here. That's correct. Okay, good. So essentially, you guys are getting the gist of it. So it's the interactions between different polypeptide chains to form together to form a more complex protein. And as someone said earlier, you can also get the attachment or adding of prosthetic groups. Okay, and a prosthetic group would be something that's not a protein, something like iron, for example, in hemoglobin. Okay, that's a prosthetic group. Okay, so essentially, it's the interaction between multiple polypeptides with the possible addition of prosthetic groups. Okay. And this question here, I got it slightly wrong. I meant what types of bonds can we get in tertiary structure? Tertiary structure, not quaternary structure. I meant tertiary structure here. So what types of bonds can we get with tertiary structure. So that's the interaction between the R groups, okay? So a lot of you guys are saying in the past questions, what types of bonds can we get with tertiary structure? So just to make that clear, I did make a mistake here. That should be tertiary structure. So let's have a few answers. Brilliant, brilliant. Okay, so a few more answers. So it's what types of bonds can we get with the tertiary structure? Okay. Good. So you guys are really nailing the types of bonds that we can get. You guys seem very confident on this side of things. Okay. So we should have four different types of bonding. We've got H bonding, permanent dipole or ionic, disulfide, and hydrophobic hydrophilic interactions. So those are the four types that we can get. So disulfide bridge, ionic interactions, hydrophobic, hydrophilic interactions, and H bonding. So those are the different types of bonds that we can get in tertiary structure. And I think, because a few of you are making a few mistakes in terms of the different structures. So what I'm going to do is I'm actually going to go back over the structures, spend another 5 minutes just talking about this again, just to make sure that you guys really understand the different levels of structure. Okay. Overall, really well done for trying to grasp these concepts. I know it's a very short period of time that we have, but you guys are doing really, really well. Okay. So, in fact, let's start from the beginning of this section. So then, so proteins are made of polypeptides, which are long chains of amino acids, and they have 4 levels of structure. So the primary structure is the order of the amino acids, okay, in the polypeptide chain. The secondary structure is hydrogen bonds between different amino acids, and then the first folding of the polypeptide chain, okay? The tertiary structure is the interaction between R groups, and those are split into our 4 types of bonds. And the quaternary structure is the coming together of more than one polypeptide, okay? So this is where we have a few, or 1 or 2, 3, 4, 5, you know, sort of polypeptides coming together to form a more complex protein, okay? So the primary structure is the sequence of our amino acids, okay? And we get the formation of these peptide bonds, okay? And I think, so I got it wrong on this slide, and I also got it wrong on the second slide. So the amide linkage, or the peptide bond, should be this. Okay, so that's the structure of a peptide bond, okay? And the production of this peptide bond forms a water molecule, okay? We can see this here. So let me get rid of all of this. So here, we've got this slightly wrong. We should take this out, okay? And because there's no other oxygen forming, that wouldn't make much sense, because we wouldn't be able to form our waters for a condensation polymerization reaction, okay? So we have the formation of our peptide bonds, which is a reaction between our amine group and our carboxylic acid group. We get water, formation of water, and here we've got a tripeptide, okay? We've got dipeptide, or also got monomers, or just amino acids, dipeptides, tripeptides, tetrapeptides, and polypeptides, okay? Then we can hydrolyze these polypeptides. We break them down back into amino acids through hydrolysis. And to do this, we need the addition of water, an acidic catalyst such as HCl. And to do this, we boil the polypeptide in water, and we include 6 moles per decimeter cubed of HCl, and we do this for 24 hours. And this way, we hydrolyze them back down into these individual constituent amino acids, okay? So the body hydrolyzes the proteins in food in a similar way, but instead of using HCl, we use proteins, okay? And these are enzymes, okay? So we use enzymes, which are different types of proteins that are used to break down these proteins, or proteases, okay? Protease enzymes. So as I said, the primary structure is the order of the amino acid, okay? The amino acid sequence, essentially. And it affects the secondary tertiary structure, and it's really important to get this right. Otherwise, any mutation, even a single wrong amino acid, can cause a particular disease or condition. The secondary structure is polypeptides fold around themselves due to the hydrogen bonding, and we get the formation of alpha helixes or alpha helices and beta pleated sheets. And we've got the examples here. So this is an alpha helix. This is a beta pleated sheet. So it's a 3D folding of polypeptides around themselves due to hydrogen bonding. Okay. Our tertiary structure is the interactions between R groups of the amino acids, okay? So they include hydrogen bonding, like we've seen here. So this is between the R groups. So if I draw out the amino acid again, so this is between the R groups. So only this portion onwards, okay, is what's this tertiary structure is about. It's the interactions between the R groups of the amino acids, okay? So it includes hydrogen bonding, like we see here. We also have hydrophobic interactions or hydrophilic interactions between different R groups. You've got dipole-dipole interactions and ionic bonding, okay? And we also have disulfide bridges, okay? And these are chains that link two sides of a polypeptide chain together, okay? This is an example of, these types of bonding in one individual polypeptide. And in reality, every protein in your body is made up of so many different complex interactions like this, but every single protein is full of these different things. And again, as I said, every single protein has, beta pleated sheets and alpha helices together as well. So it's not just, you don't just have one, you have a mixture, okay? So then, we've done these questions really well. So what we can do is we can actually move on to the next section, which is talking a bit more about enzymes, okay? About different protein structures, okay? So enzymes are proteins and they catalyze metabolic reactions, okay? So just like we were saying with, we were saying about the hydrolysis of proteins into amino acids, we've got protease enzymes, okay? They themselves are proteins, okay? But they catalyze the hydrolysis of proteins down to amino acids, for example, okay? So enzymes are proteins that catalyze metabolic reactions. They speed up reactions by 10 to the power of 10. A 2-second reaction with an enzyme would take 600 years without it. So it's really, really important that we have these enzymes in our body, because otherwise we wouldn't be able to function. So for example, everything that you do, so just moving your arm, it takes these enzymes in individual cells to make sure everything is coordinated properly and make sure every cellular reaction is taking place at a good enough speed, okay? So, this 2-second reaction with an enzyme would take 600 years without it. That is just a crazy, crazy amount of time, okay? So enzymes are specifically shaped for certain reactions, okay? And we don't need to go into the same level as biology in terms of, the active site and all this different stuff. But essentially, we don't need to go into the exact shapes of active sites and competitive inhibition and non-competitive inhibition. But essentially, enzymes are specifically shaped for certain reactions, so they only catalyze certain reactions. So one enzyme cannot do every single reaction of every other enzyme. It can only do a very, very certain reaction, a specific reaction, okay? So each reaction needs a different shaped enzyme. So we have plenty and plenty of enzymes. So there are approximately 750,000 different enzymes in the human body, and that's just the human body. But think about all the things that we can't do compared to other animals, okay? So we can't glow, green at nighttime, like certain algae can in, sorry, not algae, and like certain plankton can in the sea. Okay, and they have different enzymes, and they have loads of different enzymes to do with that. And then, for example, cows, they can eat certain things. Okay, so they have cellulase enzymes, which allow them to break down the cell walls of plants much more efficiently than we do. Okay, and even, for example, differences in enzymes between human bodies. For example, those who have lactose intolerance, they don't have the lactase enzyme past the baby stages. Okay, and that means they can't break down lactose in milk or cheese. So this means that they're unable to digest the lactose. Okay, and that's just differentiation between, you've got so many different enzymes, and even one has such a vast impact on someone's life, for example. So these enzymes are very, very, very important, and they catalyze so many different reactions, which would take absolutely ages without, and are very, very vital for our well-being and our function, of course. So here we've got a bit more on enzymes. So an enzyme structure allows for reactants to temporarily bind to them, and they hold them in the correct position to react. Okay, so it holds them in an energetically favorable shape or position for them to react with whatever is reacting with them. For example, if you've got a hydrogen atom or a H2O particle coming in, it will hold a chemical in a specific orientation to allow that water to come in and energetically bind to it very, very efficiently, allowing it to catalyze that reaction. Okay, so the places where reactants bind to are referred to as active sites. Okay, so if we have our protein, and we have an enzyme, this is the active site. Okay, so our protein binds to the active site, and the enzyme kind of engulfs it. It closes around our protein, which is here. It holds it in a position for something to come in and react with it. Okay, so if one amino acid is out of place, the active site might change shape completely, and the enzyme will no longer function. Okay, so if we have a square here, but we've got one change in, so let's say this is sugar. Okay, we've got one change in the active site. Okay, in the active site makeup, or the amino acid structure, the primary structure, it could be looking again for a circle. Okay, but this square won't fit in this circle. Okay, and that means that this enzyme is defunct. It won't work at all. Okay, so we can use this property. So if one amino acid is out of place, it might change it, but also these different bonds between the amino acid groups, these interactions between the R groups also affect the structure. So we can take advantage of that by using drugs to target the active site of enzymes and the actual structure of enzymes to alter them to make to therapeutic value, for therapeutic value. So we can alter these active sites so that they can either bind to things or can't bind to things, so temporarily inhibit them so that something doesn't get too toxic, for example. Or we might want to change the shape of something so that we can restore function to the enzyme. Okay, so if someone is genetically unable to produce the correct enzyme, the correct shaped enzyme, we might be able to provide a drug that targets the shape of the enzyme and restores its shape back to the correct active site. Okay, so we have other types of proteins as well in our body. Okay, so we've got antibodies, which are immune system proteins. I'm sure you all heard a lot about this, especially during the COVID pandemic. There's been a lot of talk about antibodies and vaccines and whether they make antibodies. We've also got contractile proteins, which are found in muscles. Okay, these aren't also just found in muscles; they're also found around cells and within cells, so they can contract and pull cells into a specific shape. Okay, we also have hormonal proteins. Okay, and these are messengers that cause a change in a cell. So we've got our testosterones, our estrogens. Those are two main examples. We've got dihydrotestosterone. We've got loads of different hormones. Okay, and those are messengers that sent from the brain or different areas of the body to act on other areas of the body and cause changes in cells. And those cells might stop producing something, might start producing something, all because of these hormonal proteins that bind onto these cells and change their function. Okay, You also have structural proteins, which support the shapes of cells and tissues. And those are things like, microtubules within cells, which kind of keep the cell a specific shape. Because of course, cells need to be specific shapes to serve their function. For example, we had our example of sickle cell anemia. Those cells, those red blood cells, are no longer the correct shape. So it's really important to maintain the shape, to maintain the function of a cell. Okay. You have storage proteins for reserves of amino acids. Then we have transport proteins, and these are proteins that move substances from one place to another. And an example of this would be, for example, in your muscle cells, or in fact in every single cell, you have a specific electric charge across the cell. And you maintain this charge by controlling the ion concentrations within the cell. And to do that, you need these transport proteins to make sure to kind of micromanage these movement of ions across the cell wall and in and out of the cell. Okay, so if you've got a cell like this, you'll have a transport protein. So this is inside the cell, this is outside the cell. You have a transport protein that allows the influx of, let's say, potassium ions. Okay, and it might also, this transport protein might also facilitate the excretion of sodium ions at the same time. You've got all these different transport proteins that maintain the membrane potentials, which is the electrical charge across a specific membrane, and that function we require that, for example, our function of nervous cells. So they need to be polarized and they depolarize in order to get an energy potential carried across, for example, from your finger into your brain. So it's really, really important that we have all these different types of proteins within our body to help us function as human beings. Without these, we wouldn't be able to function at all. Okay. So let's talk about identifying amino acids. So chromatography separates mixtures of soluble substances. So for example, if we have a mixture, like let's say you have just a colorless liquid and we want to know what's inside it, we can separate these soluble substances through chromatography. Okay, so it produces information to identify the substances in that mixture. Okay, so thin layer chromatography can be used for distinguishing between different amino acids. Okay, so we need to remember this. If you want to write this down, it's thin layer chromatography. This is the key one when we're talking about amino acids. Okay. So different amino acids will move at different rates on the paper due to their different R groups, okay, and the different charges and so on and so forth, okay. So proteins need to be broken down first, okay. So we can't just put a protein in a chromatography, in thin layer chromatography. We need to break it down into its individual amino acids first, and then we can use thin layer chromatography to understand what substances or what amino acid mixture is present, okay. And that would be through our boiling with 6 decimeter moles per decimeter cubed HCl for 24 hours. Okay, that would be how we're going to break these or hydrolyze a protein down, so that we can then use the amino acids to be used in thin layer chromatography. Okay, so here is a run-through step of how we do chromatography. Okay, so the first step is the solutions of amino acids are placed on a line. Okay, so here we've got a line. This is essentially our starting line. Okay, and then the paper is lowered into a solvent. Okay, so we'll have like a little bit of liquid here, or a little bit of solvent. Okay, and essentially what happens is, through capillary reaction, we have the liquid moving up the paper as time goes on. Okay, and this is the line here that the solvent is up to. Okay, so the solution of amino acids will start to move up through the paper with the solvent. Okay, we'll leave the paper for quite some time, for about 3 hours, and then we remove the paper from the solvent. And we mark where the solvent has reached. Okay, so we will mark here. At this point here, we need to mark. Okay, and then once it's dry, we spray ninhydrin evenly on the paper, or place under UV. Okay, and then because of this, the amino acid spots will become purple and visible, okay? And this is what we can see here. So different amino acids have different RF values, okay? And this is what we need to talk about when we're looking at chromatography. So RF values is how we can differentiate between different amino acids, okay? So by calculating an RF value, you can identify different amino acids in the sample, okay? So an RF value is calculated by the distance moved by an individual substance divided by the different distance moved by the solvent, okay? So that's why it was super important for us to measure this line here. So where the solvent got up to, it was really important for us to measure this. So we can compare this, so distance moved by the solvent and then distance moved by the amino acid, okay? Or the individual substance. So that's how we calculate an RF value. And here we've got a table full of these RF values. So we've got alanine, arginine, asparagine. We've got all these different amino acids that are representative of, well, sorry, we've got all these RF values as well that are representative of these different amino acids, okay? And what we could do is we could just have a look at our chromatography paper and measure the individual substance. We wouldn't know from the start, what each individual one would be. But if we have a look at the RF value table, we'll be able to decide which amino acids are present in the solution, okay? And that's exactly how chromatography works. So basically what we do is we calculate the RF value and then we compare it to our RF value table and find out what is inside our mixture, okay? So that completes our topics for today, okay? So what we're going to do now is we're going to summarize. We're going to go over a few questions, a few past paper questions, and if we've got any time, we can go back on a few of the other slides, okay? So, to summarize, polypeptides are long chains of amino acid, okay? And proteins are made up of polypeptides. So their order is important for the 3D structure of the protein, and a protein has 4 different levels of structure. So you've got the primary structure, which is the order of amino acids. And remember, amino acids form peptide links via the condensation polymerization reaction. And a peptide link will be this. So that's what a peptide link will look like. Secondary structure is hydrogen bonding, and we can form hydrogen bonding between these amino acids, which forms a fold in 3D space. And that fold will either be an alpha helix or a beta pleated sheet, okay? Tertiary structure is an interaction between R groups on amino acids, okay? And we can get hydrogen bonding, hydrophilic interactions, and hydrophobic interactions. We can also get disulfide bonds, or bridges, in fact, should I say. And we can also get dipole-dipole / ionic bonding, okay? We know that proteins have many functions in the body, okay? And then these peptide links can be broken down by hydrolysis, okay? And we finally just covered the fact that amino acids can be identified using thin layer chromatography, and that's the way we can differentiate between them, okay? So we've covered quite a lot there. I think it just covered up that. So we've covered quite a lot there. So we're going to go on Slido, ask a few questions. We're going to do some past paper questions, and we're going to finish off. And if we've got any time, of course, we can go over some previous slides. So the first question is, what types of proteins do we have in our body? Okay, so that was that page that we had lots of different types of proteins, and just give an example of some of these different proteins that we have. Okay. Okay, so you've got one answer here, and it's amino acids. And amino acids aren't actually proteins. Amino acids are the building blocks for proteins. So these monomers of the polypeptides, which then form proteins, okay? So we're looking at something like an enzyme, exactly. So we're looking at things like enzymes, okay? So enzymes is an example. Got structural, channel, great. Storage, transport, okay? So a channel, so that, an ion channel will be an example of a transport protein, okay? We've got a few more different types of proteins. Let's see if you guys can remember them. You've got hormonal, digestion, that's good. So a few more people. Antibodies, okay, that's really, really good. Antibodies, that's the sort of thing that we're looking for, okay. We also have contractile, that's really good. You've got contractile proteins. And that's something that we'd find, let's say, in our muscles, okay. So yeah, in total, we've got enzymes, we've got, well, this is not, fully exclusive, but we've got enzymes, antibodies, contractile proteins, hormonal proteins, structural proteins, storage proteins, and transport proteins. So enzymes, of course, catalyze reactions, and we saw that figure of, a reaction might happen in 200 years if we didn't have an enzyme. Antibodies are immune system proteins. Contractile proteins are found in muscles and individual filaments in cells. We've got hormonal proteins, which are messengers that cause a change in cells. Someone said histones, that's really good. Structural proteins support the shape of cells and tissue. Storage proteins reserve amino acids, and we've got transport proteins. Okay, so that's a really, really well answered question, guys. Really well done. So, what type of chromatography do we use to differentiate between amino acids? Let's have a few answers here. So we've got 8 people have answered. Let's have a few more before we reveal the answer. So what type of chromatography do we use to differentiate between amino acids? Is it paper chromatography, gas-liquid chromatography, thin layer chromatography, or column chromatography? Okay. I'll wait till we've got a few more answers and then we'll go over it. Doesn't matter, again, doesn't matter if you get these wrong, of course. Just make sure you write down which answer was the correct one if you got it wrong, just so you can learn for next time, okay? Or you can learn to go back and go through material to make sure that you re-jog your memory on what it was, okay? So let's have 2 more people. Let's have 2 more people answer. One more, just one more. Let's get one more person. Okay, perfect. Okay, so the correct answer is thin layer chromatography. Okay, the thin layer chromatography is a type that we use to differentiate between amino acids. Okay, gas liquid chromatography and column chromatography, they're completely different. Paper chromatography, I can understand exactly why you put that. It's something that you've probably done, but to be specific, we use thin layer chromatography. Okay. Which type of proteins can drugs target to produce therapeutic effects? Okay. Let's have a few answers on this one. This one is, I wouldn't say a trick question, but it's sort of a trick question. So we're thinking about which types of proteins can drugs target to produce therapeutic effects. Let's just talk about this from a chemistry perspective. So the main thing about what we learned, So the main type of protein that we learned about today that we can target to produce therapeutic effects. Okay, let's have 5 more people. Let's have 5 more people answer this question. If you haven't answered the question, have a guess. Have a guess. You might as well have a guess. If you don't know, just have a guess. Make sure to write down which answer is the correct one after we've gone over it. Okay, well, seeing as we're running more out of time, let's go over the answer. Well, the answer is actually every single one of these, okay? And it's interesting that you guys mostly put hormones. In fact, you can target any single one of these. In terms of chemistry, we mostly talk about enzymes, okay? We mostly talk about enzymes. But in reality, we actually can target every single one of these types of proteins. So hormones, think about contraception. You know, antibodies. We might we might actually add antibodies to someone. Transport proteins. We can sort of try and balance out specific ion concentrations. Enzymes, we might want to restore function to an enzyme so that it allows someone to process something, okay? So that is it for the Slido questions. So let's go over some exam questions, okay? Some past paper questions. So a drug is designed to simulate one of the following molecules that adsorbs onto the active site of an enzyme. Which molecule requires the design of an optically active drug? Okay, an optically active drug. So if you think about this, we're looking for something that has got a stereoisomer, essentially. So looking for something which has a stereoisomer. And if you look in detail, the only one that can have a stereoisomer is question C, okay? Because it has this OH group here and this group here, which is different, and we have a chiral carbon in the center, okay? So that's that one. So draw the structure of both dipeptides formed when phenylalanine reacts with serine. In each structure, show all the atoms and bonds in the amide link. Okay, so this one is a bit of, well, you'd need the formula sheet. So what we'll do is we'll flash this one in and we'll talk about it. Okay, so an amide link is also, so we'll flash this one in and we'll probably also flash this one in. So an amide link is also formed when acyl chloride reacts with a primary amine. Name and outline a mechanism for the reaction between CH3, CH2, CO, Cl, which are acyl chloride, and CH3, CH2, NH2, which are primary amine, okay? And give the UPAC name of the organic product. So then, let's have a look at this. And let me get rid of these. So you guys wouldn't know this one unless we had the actual formula sheet with us, okay? But we're looking at the dipeptides formed when phenylalanine reacts with serine, okay? So essentially we have our, peptide bond here and here, okay? And essentially you can have it either way. So you can either have the nitrogen group there, or you can have the carboxylic acid group on the left-hand side. And again, the same way goes. So you can either have the carboxylic acid on the left-hand side, or the carboxylic acid on the right-hand side, or the amide group or amine group on the right-hand side. So those are the two dipeptides that are formed because they are slightly different. Okay, they're dipeptide. So it's not a polypeptide; it's a dipeptide. Okay. So then, the second question was to do with acyl chlorides and primary amines, okay? And the reaction that would take place is a nucleophilic addition elimination, okay? So you're essentially adding a group onto it. So you're adding a compound onto it, but you are taking away a certain portion of it, okay? And we can go through the actual mechanism here, okay? So we have our amine group adding as a nucleophile, okay? Sorry, acting as a nucleophile. And then you have the withdrawal, and it's attacking this, you know, this carbon here, and we have withdrawal of electron onto the oxygen. And essentially what happens is this chlorine then leaves. It decides to leave. It becomes a leaving group, and we have the reinstating of an electron onto this double bond, and we have another amine attacking this hydrogen to take this away, and we have the formation of our peptide bond. Okay, so this one's slightly difficult, and it's probably the reason why I didn't want to draw it out is because it's probably a bit more easy for me to show you on an actual drawn out mechanism for you to understand a little bit better. Okay, and the name of this product would be N-ethyl propanamide. Okay, and we've used this N here because it is a little bit more complex. Okay, so that's why we've used this N to make sure that they know what we're talking about, that there is an amide group and things are bonded to it. Okay, so this question is, the following figure shows a simplified representation of the arrangement of some amino acids in a proportion of a protein structure in the form of an alpha helix. Okay, and you know this is an alpha helix not only because they tell you, but just look at the shape of it. Okay, it's essentially like a spring, and that's what an alpha helix looks like. So name the type of protein structure in this figure. Okay, so even just looking at the alpha helix, we'll be able to tell, but we can also see H bonding. Okay, we can also see H bonding between these amino acids essentially. Okay, so that confirms to us that this is secondary. This is a secondary structure. Okay, so part B is explain the origin of the interaction represented by the dotted lines in the figure above. Okay, and that's essentially our H bonding. Okay, so nitrogen and oxygen. So to get H bonding, we need to have electronegativity and the formation of dipoles essentially. So nitrogen and oxygen are very electronegative. Okay, and that means that we have C double bond O and our NH groups are polar. Okay, and this means that we get the formation of a hydrogen bond. So this means we get formation of H bonding between the oxygen and the hydrogen. Okay, and basically the lone pair on the oxygen is strongly attracted to a delta positive hydrogen. Okay, so if you think about it, we have our nitrogen. Okay, our nitrogen likes to keep its electrons with itself. Okay, it's very electronegative. Okay, and then its bond, so the electrons from this bond here are more towards the hydrogen. Okay, sorry, the nitrogen. This is delta negative, and this is delta positive. Then we've got our carbon, and we have our oxygen. Okay, now oxygen likes to keep its electrons. It's very electronegative, so it likes to keep its electrons on itself. Okay, and this double bond. Okay, so it's delta negative, And then we get this hydrogen bond between these because it's this dipole-dipole reaction essentially, and it's hydrogen bonding, okay? So those are the answers for those questions there, okay? So the amide or peptide link is found in the synthetic polyamines and also in naturally occurring proteins. So draw the repeating unit of polyamide formed by the reaction between propanadioic acid and hexane 1,6-diamine, okay? Now I've drawn this one out for you, okay? So essentially we have the formation of our peptide bond, okay? And then we have our propanadioic acid, okay? And then we have our, which would be on this side here, okay? Because we've got 3 carbons here. And then our hex 1,6-diamine would be on this side here, and it's diamine, okay? So we've got nitrogen or amine groups on both sides, okay? And we've got 6 of these, okay? Oops, I think I missed that out. So that should be 6, okay? So this is the repeating unit that you'd get, okay? So moving on to part 2, in terms of the intermolecular forces between the polymer chains, explain why polyamides can be made into fibers suitable for use in sewing and weaving, whereas polyalkenes usually produce fibers that are too weak for this purpose, okay? So this is, again, a bit more of a complex question, okay? So polyamides, we have H bonding, okay? We've talked a lot about H bonding this lesson, okay? Whereas polyalkenes are mainly held together with their van der Waals forces or van der Waals forces, okay? So H bonding is a stronger or greater than or stronger than van der Waals forces, okay? Oops. Okay, and that means that these polyamides can be used for more stressful applications, okay? And that's essentially the answer to this question. Really nice, comprehensive answer to this question. Okay. So, part B is name and outline a mechanism for the reaction between an acyl chloride and a amine group, an amine, a primary amine. Okay. So, I'm actually going to leave you guys to do this. So, I'm going to give you 2 minutes, and then we're going to talk through the reaction ourselves, okay? And it's very, very similar, because remember, we're talking about an acyl chloride here and a primary amine. So we've already done this type of reaction on a past slide, okay? So I'll give you 1 minute or 2 minutes just to roughly do it. You don't have to do it in great detail, just roughly do it, and then we'll talk it through, okay? Because this is something that we've done in the past, and I just want to make sure that you kind of, re-jog your memory, okay? I'll give you a minute or so. So this is our, we had the amine. So we had the amine acting as a, well, I'm going to give it away now, but the amine acting as a nucleophile and attacking the carbon or the carbon on the acyl chloride. We had the movement of the electron onto the oxygen in the acyl chloride. We then had the subsequent reallocation of the electron back onto the double bond, and the leaving group, or the allocation of an electron onto the chloride, so it leaves. And then we had another amide, or primary amine or secondary amine, attacking the additional hydrogen on the primary amine that's already been added, and that should produce our product, our final product. So, oops, and give the name of the product containing the amide linkage. Well, we'll go over this. So essentially this is what we have. So it's exactly the same sort of thing as last time. Okay, so we have our amine acting as a nucleophile. Okay, this is a nucleophilic addition elimination. Okay, because we're adding something to it and we're taking something away at the same time. Okay, so then so it acts as a nucleophile. We get the withdrawal of an electron onto the oxygen. Then we have the chloride being forced off and the reinstating of the electron onto the oxygen double bond. And then we actually have here, essentially, we have an electron being withdrawn onto the nitrogen from this hydrogen, and that can either be added to the chloride, so you get HCl, or it could just be from another amine. Okay, so essentially it's exactly the same reaction that we had last time. Okay, and the name, the UPAC name of this would be N-methyl propanamide. Okay, so this is it's a complex, again, it's a complex structure, so that's why we need to make sure that we put this N at the beginning of the name. Okay, so let's look at, oops, I think I've accidentally didn't hide that. But anyway, let's have a look. So part C is the dipeptide shown below is formed from two different amino acids. Okay, draw the structure of the alternative dipeptide that could be formed by these two amino acids. Okay, so let's draw this out. And essentially, it's just a reorganization of a reorganization of these amino acids. So because it's a dipeptide, this is one configuration, but we could also swap them around. Okay, we could also swap these around and we'd get this structure here. And that would also be a dipeptide using the same amino acids, okay, but it would be a different structure. Okay, it would be a different dipeptide. Okay, so it uses the same amino acids, but it's different dipeptides. So we swap these around essentially, and we've got this. So the carboxylic acid and then amine group are on different sides compared to where they were last time. Okay. Part D is the amino acids serine and aspartic acid are shown below. Give the UPAC name of serine. Okay. So the UPAC name would be 2-amine 3-hydroxy propanoic acid. Okay, it's a very, very long name. Okay, but this is going to be the UPAC name for it. Okay, so part 2 is draw the structure of the species formed when aspartic acid reacts with aqueous sodium hydroxide. Okay, so essentially we're looking at, we have a Zwitter ion in terms of the serine, because amino acids are Zwitter ions, and we're looking at aqueous sodium hydroxide, which is a strong base. Okay, so it's going to go more acidic, which means that we're going to get deprotonation, and we'll get the formation of this ion here. Okay, so we get deprotonation. So our nitrogen doesn't gain a proton, but our carboxylic acids release their protons. Okay, to form acids. Okay. Part 3 is draw the structure of the species formed when the serine reacts with dilute hydrochloric acid. Essentially, this is the same thing, but just in the opposite direction. Okay, so we get protonation. Okay, and we get the formation of this. Okay, so we've got the positive NH3. Okay, so we've got protonation here, and we have our carboxylic acids still the same. And then the final bit is draw the structure of the species formed when the serine reacts with an excess of bromomethane. Okay, and I forgot to draw this one out clearly, and we get this one here. Okay, we get bromomethane, and we get the formation of this particular structure here, okay? So then, oh, no, I did. So then we'll go to a final question, which is sort of a longer question, but it's not actually that hard, okay? So a peptide is hydrolyzed to form a solution containing a mixture of amino acids. So the mixture is then analyzed by silica gel, thin layer chromatography using a toxic solvent. The individual amino acids are identified from their RF values. So part of the practical procedure is given below. So 1 is wearing plastic gloves to hold a TLC plate. Draw a line 1.5 centimeters from the bottom of the plate. 2 is use a capillary tube to apply a very small amount of the solution of amino acids to the midpoint of the pencil line. 3 is allow the spot to completely dry. 4, in the developing tank, add the developing solvent to a depth of no more than 1 centimeters. 5 is place your TLC plate in a developing tank. 6, allow the developing solvent to rise up to the plate, up the plate to the top. 7 is remove the plate and quickly mark the position of the solvent front with a pencil. And then 8 is allow the plate to dry in a fume cupboard. Okay, so question A or question 10A, parts of the procedure are in bold text. For each of these parts, consider whether it is essential and justify your answer. Okay, so the first one is in bold, is wearing plastic gloves to hold TLC plates. Okay, and so gloves is essential. Okay, and this is to stop contamination. Okay, of course you might have all sorts in your hands, and you want to make sure that this is a specific procedure looking at a solution containing a mixture of amino acids. Okay, we want to make sure that there's only those amino acids. So the next part is a depth of no more than 1 centimeters. Okay, let's just shorten that to depth. Okay, this is essential again, and this is because we don't want too deep, otherwise it will dissolve the mixture from the plate. Okay, we don't want it too deep, or it will dissolve the mixture. Third one is allow it go to the top. This is not necessary or not essential, okay? And this is because the RF value can be calculated just by using wherever the solvent front goes. Oops, wherever solvent front is. And the final one is allow the plate to dry in a fume cupboard. Fumes. And this is essential because it's toxic, okay? The solvent is toxic. So then, part B is outline the steps needed to locate the positions of the amino acid on the TLC plate and to determine their RF values. Okay, so the first one is to spray it with ninhydrin or developing agent, whichever one you say. Develop agent. Or you could also say UV light. That's the first step. Second step is to measure distances. Between the spots, and so the initial pencil line to the spots, the initial pencil line to the solvent front. And then the third step is to calculate the RF, which is the spots, distance of the spots over distance of the solvent front. Okay. That's essentially what it is, okay? And then C, explain why different amino acids have different RF values. Well, different amino acids have different polarities. and therefore they'll have different retention on the stationary phase. Well, they'll have different solubility. Okay, therefore they have different solubility. Okay, so that actually concludes our lesson for today. So we've done all the past paper questions, done all our learning objectives, we've done all our Slido quizzes. So because we've run over, unfortunately, we don't have any more time to go back over those slides that we talked about earlier. But of course, you do have the presentation. So if you want to have a look at those slides again, you're more than welcome to. So we described polypeptides as a sequence of amino acids joined by peptide links and drawn peptides from amino acids. We explained the formation of the primary, secondary, tertiary structures of proteins. We know that peptide links can be broken by hydrolysis, producing the constituent amino acids. We understand the importance of hydrogen bonding and sulfur bonds or sulfide bridges in proteins. We know the properties and functions of proteins, and we can describe how amino acids can be separated and identified by thin layer chromatography. Okay, so that concludes our lesson for today. So what I will say is we'll see you in about a month's time. Hopefully you guys will come back for that. I really enjoyed teaching you. So I'll look forward to seeing you guys next session in about a month's time. There might also be a revision session coming up soon, which I highly recommend if you want to go over some topics quickly. So without further ado, goodbye, and I hope you have a nice Sunday. We've done a lot of chemistry today, so hopefully you have a nice relaxed Sunday to finish off the day. Okay, thank you so much, and I'll see you next time.